Welcome to night cosmos sleep. Could a speck of dust, so small that it is almost impossible to see, destroy an entire interstellar spacecraft? At 10 or 20% of the speed of light, even the smallest piece of matter can carry an enormous amount of energy. Upon impact, the dust particle and part of the spacecraft's surface could melt, vaporize, turn into plasma, and produce fragments capable of penetrating deep into the vessel. But the danger does not come from a single collision alone. Over decades of travel, countless tiny particles could gradually erode windows, shielding, electrical systems, and radiators. To understand how serious this threat truly is, we will begin with the traces that spacecraft have already brought back to Earth. On a metal surface that appeared almost completely intact, a hole only a few millimeters wide stood out as a tiny dark spot, small enough to be overlooked unless someone leaned in for a closer look. Around its rim, the metal was bent, darkened by heat, and marked by an intense burst of heating that had occurred in far less time than the blink of an eye. That metal panel had once been part of the radiator system aboard the Space Shuttle Endeavour. After the spacecraft returned to Earth, the panel was removed and inspected along with thousands of other components. No footage captured the moment of impact, no witness saw the object approaching, and no radar system tracked its path. All that remained was a small crater surrounded by altered material along its edge, like a quiet scar telling the story of an event that had taken place in space. The scar was not large, but it was enough to show that an almost invisible object could still leave a clear mark on a vehicle built to withstand an extreme environment. Analysis suggested that the object responsible for the puncture may have been only about 1.6 millimeters across, far smaller than most pebbles on the ground and only slightly larger than a coarse grain of sand. Yet when it struck Endeavour, it may have been traveling at nearly 9 kilometers per second. At that speed, the object could cross the length of a football field in a tiny fraction of a second. When it hit the radiator panel, it created an entrance hole about 6 millimeters wide and passed through the material. An object smaller than the tip of a fingernail left damage many times larger than its original size. The puncture on Endeavour was not an isolated case. Over decades of operation, engineers found thousands of impact marks on the windows, radiator panels, wings, and protective outer surfaces of the space shuttle fleet. Most were no more than pinprick-sized craters or faint scratches in the coating. Others penetrated more deeply into glass and metal, forcing the affected components to be replaced before the next flight. Each mark was evidence that the region of space around Earth is not as empty as it appears. From inside the cockpit, the shuttle's windows looked thick, clear, and extremely strong. Yet after every mission, their surfaces were examined under bright lights for microscopic pits that could easily escape the naked eye. Some marks were only fractions of a millimeter wide and, at first glance, looked no different from specks of dust on the glass. Under magnification, they appeared as miniature craters, with tiny fractures spreading outward from the center, revealing that a significant amount of energy had once been transferred into that exact point. Not every object responsible for these scars was a natural rock arriving from deep space. In the orbital region around Earth, there are two main sources of small material that can cross a spacecraft's path. The first is micrometeoroids, natural particles of rock and dust originating from comets, asteroids, or material left over from the formation of the solar system. The second comes from human space activity itself, created by vehicles launched into orbit over many decades. A flake of paint peeling from a rocket stage, a fragment of metal from an old satellite, a piece of insulation, or debris produced by an earlier collision can continue orbiting Earth for years. These objects may be extremely small, but their orbital speed means they are no longer harmless. A spacecraft in low Earth orbit is already moving around the planet at nearly 8 kilometers per second. If a piece of debris is traveling in the opposite direction or crossing its path, the relative speed between the two objects can exceed 10 kilometers per second. On the ground, a flake of paint weighs almost nothing and can be carried away by the wind. In orbit, that same fragment can create a small crater in glass or penetrate a thin metal layer if the impact angle and velocity are high enough. What makes these tiny objects especially concerning is not only the energy they carry, but also the fact that they are nearly invisible to tracking systems on Earth. Radar can detect many satellites, rocket stages, and larger pieces of debris moving around the planet. Their orbits are calculated, updated, and compared with the paths of active spacecraft. When an object may pass too close to the International Space Station, control teams can assess the danger and prepare an orbital adjustment maneuver. The station does not need to move very far to avoid an object. A very small change in velocity, made early enough, can cause the two paths to be separated by hundreds of additional meters at their closest approach. However, that ability to maneuver out of danger exists only when the object has already been detected and its orbit can be predicted. A fragment only a few millimeters wide, or smaller, usually does not reflect enough radar energy to be tracked individually from the ground. It is also too small, too dark, and moving too quickly for onboard cameras to detect from a safe distance. By the time light reflected from it reaches a sensor, if that happens at all, the remaining time before impact may be so brief that no evasive maneuver could change the outcome. A spacecraft must therefore continue flying through an environment filled with countless objects whose exact positions cannot be known. Engineers cannot guarantee that every particle of dust and every fragment of debris will pass harmlessly by. They can only estimate the probability of impact, identify the most vulnerable areas, and place protective layers in front of them. The spacecraft is not designed to eliminate every possible effect, because such a goal would be nearly impossible to achieve. What matters more is preventing a minor impact from developing into an incident serious enough to cause a loss of pressure, an electrical short circuit, a failure of the cooling system, or the end of the entire mission. A safe spacecraft is not necessarily one without scratches, but one that continues to function after those scratches appear. The International Space Station is surrounded by several kinds of protective structures, especially around the modules where people live. Each area is shielded according to the direction from which debris is most likely to arrive, the thickness of the station's walls, and the importance of the equipment behind them. Its windows are made from multiple layers of glass, while the pressurized compartments are protected by structures designed to break apart and disperse an incoming object before it reaches the wall, holding the air inside. Even so, a structure as large as the space station cannot be enclosed within an infinitely thick shell of metal. Every protective layer adds mass. All of that mass must be carried into orbit by a rocket, so the thicker the shielding becomes, the more energy and money are required to launch it. If the protective structure becomes too heavy, the spacecraft must carry less scientific equipment, water, food, fuel, or fewer of the other systems it needs. Spacecraft design is always a balance between surviving the environment and accomplishing the mission. A thicker metal panel may stop more objects, but it cannot guarantee protection against every size, every impact angle, and every possible velocity. Each protective approach must be chosen according to the hazards most likely to occur. Rather than trying to build a spacecraft that will never be damaged, engineers generally accept that small dents and scratches will appear throughout its operational life. What they must ensure is that this damage does not reach critical systems. A dent in an outer shield may be nothing more than a mark left by the journey. A hole that penetrates a pressurized compartment, storage tank, or coolant line could have far more serious consequences, even if the opening itself is small. Not every collision is detected when it happens. A tiny particle can damage the outer surface without causing any obvious change in the spacecraft's operation. Pressure may remain stable, the equipment may continue working, and the crew may never realize that a small area of the surface has just been damaged. Only after the vehicle returns to Earth, beneath the bright lights of an inspection facility, does the mark become clearly visible. The space shuttle's radiator panels were especially valuable for studying this phenomenon. They covered a large area, were regularly exposed to the space environment, and could be returned to the ground for direct analysis. Each crater preserved part of the story of the object that struck it, including its direction of travel, energy level, material composition, and the way the impact spread through the structure. These small marks helped engineers understand what had happened while the spacecraft was operating in orbit. In some cases, a tiny amount of the impacting material remained trapped around the rim of the crater. The chemical composition of this residue could help distinguish a natural dust particle from a fragment created by human activity. Silicate-rich traces could suggest an origin in cosmic dust, paint, metal alloys, or artificial insulation materials could indicate that the object came from a satellite, a rocket stage, or another vehicle that had once operated in orbit. Whether the impacting particle came from a distant comet or an inactive spacecraft, the basic mechanism of damage remained the same. The object carried kinetic energy, and when it was brought to a sudden stop across a very small area, that energy had to be transferred into the spacecraft's material. The metal could be compressed, torn, and intensely heated. The incoming object could shatter into smaller fragments, while part of it, along with part of the spacecraft's surface, could melt or turn into vapor. Shock waves traveled into the layers beneath, causing the final damaged area to become much larger than the particle's original size. This is why an object only a few millimeters wide could still produce a hole larger than itself and affect structures buried more deeply below the surface. All of these effects occur at velocities that modern space engineering has become relatively familiar with, usually ranging from several kilometers per second to more than 10 kilometers per second. Even this environment is harsh enough to require spacecraft to carry specialized shielding. Vehicles also need orbital tracking networks, risk assessment procedures, and careful inspections after every flight. An interstellar spacecraft, however, would not simply travel a little faster than one orbiting Earth. Suppose a probe were accelerated to 20% of the speed of light. It would be moving at nearly 60,000 kilometers per second. In a single second, it could travel a distance equal to roughly 1.5 trips around Earth. Compare with the impact on Endeavour at nearly 9 kilometers per second. The relative velocity could be thousands of times greater. The dust particle ahead would not need to be moving toward the spacecraft, because the spacecraft's own speed would be enough to turn the encounter into an extraordinarily violent collision. The particle could be almost motionless within the interstellar medium. Yet from the spacecraft's frame of reference, it would appear to be rushing toward the vessel at nearly the same speed as the spacecraft itself. A distance of 1,000 kilometers would disappear in less than 0.02 of a second. Once the particle was only 1 kilometer away, the time remaining before impact would fall to just a few tens of millionths of a second. No ordinary camera could detect the object, determine its trajectory, and steer the entire spacecraft aside within such a brief interval. Even if a sensor recognized the dust particle, the information could not be processed and converted into an evasive maneuver quickly enough. An interstellar spacecraft would therefore face the same kind of problem encountered by the Space Shuttle and the International Space Station, but at a far more extreme level. It could not know the exact location of every particle ahead. Nor could the spacecraft stop during the journey to replace a window, repair its shielding, or return to a maintenance facility. Every protective structure would have to continue working for years without direct assistance from Earth. A journey to the nearest star system could last more than 20 years, even at 20% of the speed of light. Across a distance of more than 4 light-years, the spacecraft would have to remain on course, maintain a stable temperature, and protect the equipment behind a forward section that was continuously sweeping through the interstellar medium. Every small particle it encountered could leave a mark. Most of those marks might not be serious, but after many years, the protective material would no longer look the way it did when the spacecraft left the solar system. The hole, only a few millimeters wide in Endeavour, did not destroy the spacecraft. It merely left evidence that an extremely small object could concentrate enough energy into an area smaller than a fingertip to penetrate metal. Yet that mark also raised a much larger question. If an object about 1.6 millimeters wide could pierce a radiator panel at nearly 9 kilometers per second, how much would the outcome change when the velocity increased to almost 60,000 kilometers per second? The answer cannot be based on the particle's size alone, because a small object does not necessarily carry little energy when it is moving fast enough. When velocity increases by thousands of times, the collision no longer resembles a pebble striking metal. It can become an event in which the dust particle and part of the spacecraft's surface are crushed, heated, and transformed before the material has time to respond in familiar ways. At that moment, the boundary between the impacting object and the spacecraft's surface may disappear into a cloud of violently heated matter. The size of the particle has barely changed, but the speed at which the distance between it and the spacecraft closes has transformed the entire nature of the encounter. When that distance disappears thousands of times faster, Mass is no longer the only factor determining the danger. Most of the power of the collision now lies in motion. And to understand how much energy a tiny dust particle can carry, we must look more deeply into the very speed carrying the spacecraft toward the stars. A grain of dust resting on a fingertip is almost incapable of causing harm. It is so light that a single breath can lift it from the skin, carry it across a room, and let it disappear without leaving a trace. But that harmlessness exists only when the dust particle and our bodies are nearly motionless relative to one another. If that same particle appears in front of a spacecraft traveling at 10 or 20% of the speed of light, the nature of the encounter changes completely. The particle remains just as small, and its mass does not increase in any way the eye could notice, but the relative velocity transforms it into a concentrated amount of energy delivered across an extremely narrow area of the spacecraft's surface. This leads to a question that is more difficult than it first appears. How small must a particle be before it is truly harmless? Diameter alone cannot provide the answer, because two particles of the same size can have very different masses if they are made from different materials. A dense, metallic grain will weigh considerably more than a porous particle composed of carbon or ice. Speed is just as important as mass. A large object moving slowly may be less dangerous than a tiny object moving at an extreme velocity. On Earth, we often judge danger by size because the objects around us do not usually move fast enough to make our intuition unreliable. In space, especially during an interstellar journey, that intuition can no longer be trusted. A dust particle may be far too small to see, but if the distance between it and the spacecraft closes at tens of thousands of kilometers per second, the energy released during impact can be far greater than its size would suggest. At familiar velocities, kinetic energy increases approximately with the square of speed. When the speed of the same object doubles, its energy does not merely double, it increases by about 4 times. If the speed triples, the energy rises by nearly 9 times, even though the object's mass remains unchanged. This principle explains why a car traveling only somewhat faster requires a much longer distance to stop. It also explains why small pieces of orbital debris can cause serious damage, but as velocity approaches the speed of light, the classical calculation begins to lose some of its accuracy. At 10% of the speed of light, relativistic effects are still not very large, but they are significant enough to matter when precise numbers are needed. At 20% of the speed of light, the difference becomes more noticeable. The actual energy is slightly higher than the value produced by the familiar formula from classical physics. To get a sense of the scale, consider a hypothetical particle with a mass of 1 microgram. A microgram is 1/millionth of a gram, so small that a person would barely feel it resting on the skin. This is not meant to represent every grain of interstellar dust, but simply to provide an example that is easy to follow. If that particle encountered a spacecraft traveling at 10% of the speed of light, its impact energy would be about 453 kilojoules. That is an enormous amount of energy for an object weighing only 1/millionth of a gram, especially when all of it is transferred into a surface area that may be only a fraction of a millimeter wide. When the speed rises to 20% of the speed of light, the energy of the same dust particle reaches about 1.85 megajoules. Simply doubling the velocity increases the energy by more than 4 times, while reducing the travel time to a nearby star system by only about half. An energy of 1.85 megajoules can be compared with the chemical energy released by roughly 0.44 kilograms of TNT. This comparison is only meant to convey the scale, because the dust particle is not a bomb and does not explode through a chemical reaction. It contains no explosive material, has no trigger, and does not produce a fireball in the familiar sense. The energy is released when the particle's motion is brought to an almost instantaneous stop against the spacecraft's surface. Part of that energy deforms the material, part becomes heat, and part causes the particle and the spacecraft's surface to melt or vaporize. The rest may spread outward as shock waves, plasma, fragments, and secondary radiation. How that energy is distributed matters just as much as the total amount. If 1.85 megajoules were spread evenly across a broad shield, the consequences might be easier to control. But a dust particle does not distribute its energy across a large area at first. It delivers it into a tiny point of contact over an extremely short interval. That concentration prevents the material at the impact site from conducting heat into the surrounding structure quickly enough. Temperature and pressure rise faster than metal, glass, or composite materials can respond in ordinary ways. Before the rest of the structure has time to absorb the energy, the contact region may already have been completely disrupted. However, a particle with a mass of 1 microgram is larger than most interstellar dust grains believed to be common. If this example were taken on its own, it could create the false impression that every centimeter of the flight path is filled with objects carrying energy comparable to a significant amount of explosive material. The space between stars is far more diffuse than that. Most dust particles have much smaller masses, sometimes thousands or millions of times below the example above. The energy of each individual impact is therefore lower by a similar proportion. Some particles may only produce tiny pits, strip away a surface coating, or cause localized damage without penetrating deeply into the spacecraft. But interstellar dust does not exist in a single size. Models must account for a broad range, from extremely small and very common grains to larger particles that are much rarer. It is the rare tail of that distribution that creates the greatest uncertainty for interstellar spacecraft design. A spacecraft may pass through billions of very small particles and continue operating, even as its surface is gradually eroded. Yet a single particle, many times larger than average, could deliver hundreds or thousands of joules into one precise location. For a large spacecraft, that may become a damaged area that the shielding must absorb. For a probe weighing only about 1 gram, several kilojoules would no longer be a minor incident. The entire spacecraft might weigh about as much as a paperclip, while still needing to carry a camera, computer, navigation sensors, power source, and communications transmitter. There would be almost no room for protective material. If the impact struck a sacrificial shield designed to absorb damage, the probe might continue flying. If the same energy traveled directly into the processor or camera, the entire mission could end even if the rest of the spacecraft remained physically intact. A vehicle does not need to break into pieces to be considered destroyed. Losing the ability to determine its orientation would be enough to prevent it from pointing its instruments toward the target. A damaged memory system could erase all of the data it had collected. The loss of a laser transmitter or antenna could leave every image of the destination star system trapped forever aboard a device no longer able to communicate with Earth. Impact energy is therefore only the first step in assessing the danger. The outcome also depends on the particle's mass and density. A small metallic grain may weigh more than a silicate grain of the same size, while a porous particle may break apart more easily before transferring all of its energy into a single point. The angle of impact also changes the result. A particle striking the nose of the spacecraft head-on will usually concentrate its energy in a direction that drives deeper into the structure. If it arrives at an oblique angle, some of the energy may be drawn along the surface, producing a long groove or stripping away material instead of creating a straight puncture. The material at the front of the spacecraft determines how the energy is absorbed and dispersed. A soft metal may deform and melt differently from a brittle ceramic. Carbon, graphite, quartz, aluminum, and composite materials each have their own strengths and limitations when exposed to hypervelocity impacts. The thickness of the protective layer is only one part of the design. A thick shield can retain more incoming material, but it also makes the spacecraft heavier and more difficult to accelerate. If all the energy is confined within an area that is too small, even a thick shield can be intensely heated or produce fragments from its rear surface. The distance between the shield and the equipment inside also has a direct effect on survivability. If sensitive components are placed too close to the surface, fragments and shock waves may reach them before they have time to disperse. A suitable gap allows the expanding cloud of material to spread outward and reduce the concentration of energy. The exact location of an impact can sometimes determine the entire outcome. The same particle may leave only a dent if it strikes a heavily shielded region, yet end the mission if it hits the edge of a camera, a power line, or the junction between two layers of material. The probability of encountering a dust particle cannot be separated from the probability that it will strike a vulnerable point. The size of the spacecraft also creates a paradox. A large vehicle has a broader frontal area, so it sweeps through more space and is more likely to encounter more particles. In return, it can carry thicker shielding, multiple backup systems, and isolated compartments designed to contain damage. A smaller spacecraft encounters fewer particles because its frontal cross-section is narrower, but each collision affects a larger fraction of its total structure. A crater only a few millimeters wide may be almost insignificant on a spacecraft hundreds of meters long, yet cover much of the surface of a probe only a few centimeters across. Whether the energy spreads outward or remains concentrated therefore becomes a critical factor. If the shield causes the particle to break apart into an expanding cloud of fragments, the rear wall may absorb the load across a wider area. If the particle maintains a concentrated stream of motion, it may continue boring deeper into the inner layers. This is why a single energy value cannot tell us with certainty whether a spacecraft will be penetrated. Two impacts with the same total energy can produce very different outcomes. One may only strip away the outer surface, while another destroys equipment buried deep inside. The level of danger also depends on the duration of the journey. A single collision may be insignificant, but a shield eroded over 20 years will respond differently from one that was still intact when the spacecraft first left the solar system. Earlier damage may create weak points for later impacts. An interstellar spacecraft must therefore withstand not only the largest particle predicted by current models, but also preserve its protective ability after millions or billions of smaller strikes. Each particle removes only a tiny amount of material, yet no shield has infinite thickness. The challenge becomes even greater because protective mass competes directly with the mass available for scientific instruments. Adding 1 gram of shielding to a spacecraft that weighs 1 gram doubles its total mass. The propulsion system must then supply more energy to reach the same velocity, changing the entire design. Reducing speed may make each collision less violent, but it lengthens the journey and requires the equipment to keep working for more decades. Increasing speed shortens the flight, but gives every gas atom and dust particle ahead more energy. No choice comes without a cost. A tiny dust grain can carry an enormous amount of energy, but that energy alone does not automatically determine whether the spacecraft will be destroyed. The result depends on how the material receives the impact, how heat and pressure spread through the structure, and whether the fragments are contained or continue penetrating deeper inside. At lower velocities, it is still possible to imagine a solid particle striking a metal plate and coming to a stop. Once the speed becomes high enough, that image is no longer accurate. Both the dust grain and part of the spacecraft's surface may lose their solid state almost as soon as they touch. Within a few millionths of a second, matter is compressed, heated, and disrupted faster than human beings could ever observe directly. The boundary between the dust particle and the shield begins to blur within a region of intensely heated material where metal, vapor, and charged particles start to merge together. Speed has transformed a lightweight particle into a concentrated packet of energy. But to understand what that packet truly does to the spacecraft, we must enter the brief instant when matter no longer behaves like a bullet striking a wall and begins turning into plasma. In a vacuum, no sound of an explosion travels outward as it would through an atmosphere. An observer watching from a distance might see only an extremely brief flash at the spacecraft's nose, followed by a small region of material disappearing from its surface. Behind the point of impact, a cloud of hot vapor, fragments, and charged particles would begin expanding into the deeper layers of the structure. The event unfolds far too quickly for the human eye to follow directly. The dust grain no longer behaves like a pebble striking a sheet of metal, and the spacecraft's outer shell does not simply dent inward and spring back. At sufficiently high speeds, both objects can be crushed, melted, and transformed almost the instant they touch. The question is therefore no longer simply whether the dust particle can penetrate the shield. Before we can know how deeply it will travel, we must understand whether the particle still exists as a solid object at the moment it reaches the spacecraft, or whether it has already become part of the violently heated cloud of matter forming around the impact site. To search for answers, engineers do not begin with a spacecraft traveling close to the speed of light. They begin in laboratories built to produce hypervelocity impacts, where very small projectiles are accelerated fast enough to recreate some of the conditions spacecraft experience in orbit. At testing facilities operated by NASA and ESA, one device commonly used is a two-stage light gas gun. Unlike a conventional firearm, it does not use propellant to drive a projectile directly through the barrel. Instead, an explosion or compressed gas first pushes a piston, which then compresses a light gas such as hydrogen or helium to an extremely high pressure. When a diaphragm at the front ruptures, the compressed gas expands and drives the small projectile down the barrel. Because hydrogen and helium have low molecular masses, they can transfer energy very efficiently, allowing the projectile to reach speeds of around 6 to 7 kilometers per second in some test configurations. That is still only a tiny fraction of the speed imagined for an interstellar spacecraft, but it is already enough to make the collision behave very differently from an ordinary bullet impact. Test projectiles can be fired into aluminum, steel, composites, glass, solar panels, pressure vessels, or layers of material used in spacesuits. High-speed cameras record the moment of impact in frames so brief that millions of them would be needed to make up a single second. Sensors measure pressure, temperature, penetration depth, and the size of the damaged region. Afterward, the material is cut open, examined under microscopes, and analyzed to determine which areas melted, which vaporized, and how deeply the fragments traveled. In one test published by ESA, an aluminum sphere about 2.8 millimeters in diameter was fired into a shield at nearly 7 kilometers per second. It was much smaller than a marble and so light that it would seem almost insignificant in the palm of a hand. Yet when it struck the metal plate, the aluminum sphere no longer retained its original shape. At the instant of contact, the pressure rose far beyond the ordinary limits of the material. The aluminum sphere was flattened, shattered, and mixed with metal, torn from the shield. Some of the matter was crushed into extremely small fragments, some melted, and some reached temperatures high enough to become vapor. The result was not an intact projectile resting inside a hole. Instead, it left behind a crater, a region of altered metal, and a cloud of debris continuing in the original direction of travel. The collision lasted only an extremely short time, yet its energy triggered several processes almost simultaneously. First, the incoming particle was decelerated with extraordinary force. It could go from several kilometers per second to nearly motionless over a distance of only a few millimeters. That sudden change in velocity created immense pressure at the point of contact, enough to exceed the compressive strength of both the particle and the shield. The material no longer had time to bend and distribute the force in the familiar way. The bonds holding atoms together within the solid structure were disrupted faster than heat could spread into the surrounding area. The small region at the point of impact was compressed, heated, and deformed before the rest of the shield had time to respond. Part of the energy became heat, causing material to melt or vaporize. Another portion created shock waves that traveled into the metal. Small fragments continued moving forward, striking the material behind the first layer and creating new hot spots. So the destructive process did not end at the outer surface. When the temperature and pressure became high enough, some atoms lost their electrons. The matter was no longer an ordinary neutral gas, but a plasma composed of positively charged ions and free electrons. This plasma cloud might exist for only a very brief time, yet still last long enough to produce a flash of light and affect electrical equipment near the impact site. Plasma is not an exotic substance found only inside stars. It appears whenever matter receives enough energy for electrons to break free from their atoms. Lightning in the atmosphere, the glow inside a neon lamp, and most of the visible matter in the sun are all different forms of plasma. During a hypervelocity impact, plasma forms across a very small region and quickly disappears as it expands, cools, or recombines into neutral atoms. Before that happens, however, the charged particles can create electromagnetic pulses, alter the electrical potential across the surface, and interfere with sensors or electronic circuits. The danger, therefore, does not come only from the crater visible after the collision. An electronic device may be affected even if it is not located directly along the particle's path. If the electrical pulse is strong enough, or occurs near a sensitive conductor, it can corrupt data, force a processor to restart, or damage a component. Shock waves traveling through the material can also cause damage far from the point of impact. When the particle strikes the outer surface, it creates an intensely compressed region that moves through the metal. The atoms themselves do not travel all the way through the shield, but their motion transfers pressure from one layer to the next. When the compression wave reaches the inner surface of the metal plate, it encounters the boundary between the solid material and the empty space behind it. There, part of the wave reflects in a way that can create tensile stress within the structure. Metal that withstands compression relatively well may be much weaker when pulled apart over an extremely short period. As a result, part of the material on the inner surface can break away from the shield and fly into the spacecraft, even if the original particle never fully penetrated the outer wall. This effect is commonly called spallation. It can turn a wall that appears intact into a source of dangerous fragments on the protected side. It is somewhat like striking one side of a rock with a hammer. The surface being hit does not necessarily have to break through, yet a piece on the opposite side may still crack loose and fall away. Inside a spacecraft, fragments torn from the inner surface could travel fast enough to damage wiring, storage tanks, or nearby equipment. If a crude compartment lies behind the shield, small pieces of metal may become dangerous even without a direct opening to the vacuum outside. They could cut through insulation, puncture pipes, or strike an astronaut. An impact against the outer hull can therefore cause injuries and damage inside without leaving a fully penetrating hole. This is why engineers do not simply measure whether the projectile passes through the shield. They also inspect the rear surface, collect the fragments, and determine how much material has broken away. A shield may stop the projectile and still be considered unsafe if it produces too much secondary debris on the inside. At test velocities of around 6 or 7 kilometers per second, these processes are already remarkably complex. The incoming particle can melt, vaporize, ionize, and generate shock waves within only a few millionths of a second. Yet a hypothetical interstellar spacecraft traveling at 20% of the speed of light would be moving almost 10,000 times faster. The gap between laboratory data and interstellar velocity is so vast that results obtained at 7 kilometers per second cannot simply be extended along a straight line to nearly 60,000 kilometers per second. Materials may enter entirely different response regimes, where deep ionization, secondary radiation, and particle-level processes become far more important. No laboratory today can fire a macroscopic dust particle into a shield at 10 or 20% of the speed of light. Particle accelerators can push protons, electrons, or extremely small ions to near light speed, but that is very different from launching a dust grain made of billions upon billions of atoms into a large sheet of material. For that reason, much of what we understand about dust impacts at interstellar velocities must come from physical models, computer simulations, and extrapolations built from data gathered at lower speeds. These models can describe how energy enters a material, but their accuracy still depends on how well that material's properties are understood under conditions that have never been tested directly. At interstellar speeds, even a single hydrogen atom is no longer entirely harmless. From the spacecraft's frame of reference, that atom strikes the nose with energy comparable to a particle inside an accelerator. A very thin stream of gas, encountered at a high enough velocity, becomes a continuous bombardment of protons, electrons, and ions. Protons can penetrate the material and lose energy through collisions with electrons and atomic nuclei. High-energy electrons can emit braking radiation as they slow down. Heavier ions leave behind dense trails of ionization, altering crystal structures and causing cumulative damage within the shield. Unlike a large dust particle that produces a clearly visible crater, interstellar gas acts almost continuously across the entire leading edge. Each individual particle carries far less energy than a large grain of dust, but there are many more of them. Over the years, they can heat the surface, change the material, and create a radiation environment inside the spacecraft. Some of that radiation is produced the moment the energetic particles are brought to a stop. A thicker shield can absorb more particles, but it can also generate more secondary radiation when those particles collide with atoms in the material. Increasing thickness, therefore, does not always reduce every danger by the same proportion. If the shield is made from heavy elements, it may stop some kinds of particles effectively, while producing more braking radiation as high-energy electrons pass through. Lighter materials may reduce certain forms of secondary radiation, but they require greater thickness to absorb the same amount of energy. Every choice involves a trade-off. Heat must also be carried away from the impact region. During a single collision, much of the heated material may vaporize outward into space. But when interstellar gas continuously bombards the leading edge, the spacecraft must manage a sustained flow of heat. If that heat is not conducted toward radiators, the temperature of the shield and the equipment behind it will gradually rise. The front of the spacecraft may never be fully penetrated, yet sensors nearby can still be disrupted by plasma and electrical charge. Insulation may degrade under radiation, while electronic circuits accumulate errors caused by energetic particles. A shield that retains its shape does not necessarily protect every function inside. This changes what it means for a spacecraft to survive. It may have no large punctures, remain in one piece, and continue along its original trajectory. While its camera loses sensitivity, its computer suffers repeated errors, or its communications system becomes unstable. Mechanically, the spacecraft may still exist, but as a mission, it may already have failed. A dust grain that has been stopped does not simply disappear. Its kinetic energy must be converted into other forms. Some becomes heat, some deforms the material, and some produces plasma, shock waves, fragments, and radiation. The shield only changes where that energy is released and how it spreads. If all the energy remains concentrated at one small point, the shield may be penetrated deeply. If the particle is broken apart early and the debris cloud has time to expand, the impact load can be distributed across a broader area. The rear wall then has a better chance of absorbing the energy without being completely destroyed. The debris cloud may have only a millionth of a second to expand, yet that can still make the difference between a direct puncture and a shallower region of damage. The gap between the first shield and the main wall therefore becomes an important part of the design, even though the empty space may not appear protective at first. A single solid wall gives the dust particle one place to release all of its energy. A multi-layer system can break the particle apart first, allowing vapor, plasma, and fragments to spread before reaching the more important structure behind it. That dispersion can reduce the concentration of the impact. However, the gap also makes the spacecraft larger, while the additional layers increase its mass. For vehicles orbiting Earth, this is already a difficult engineering problem. For an interstellar spacecraft that must reach tens of thousands of kilometers per second, every gram of protective material significantly increases the energy required for acceleration. No shield can make the energy disappear. A good design simply forces it to follow a less dangerous path. Where some material is allowed to be sacrificed, fragments are allowed to spread, and sensitive equipment is placed far enough from the first point of impact. A very rigid wall, therefore, is not necessarily the best answer. If it stops the particle but produces plasma, heat, and fragments directly beside the computer, the spacecraft may still lose its ability to function. Survival depends on how the entire structure works together to control the consequences after impact. In the instant when the dust grain reaches the spacecraft's nose, matter may no longer resemble a solid particle confronting a metal plate. It becomes a region of extreme pressure, hot vapor, plasma, and shock waves expanding through several layers of material. The collision ends within a millionth of a second, but the damage it leaves behind may determine the fate of a journey lasting decades. To survive, the spacecraft needs more than a wall hard enough to withstand the blow. It needs a structure designed to break apart the dust particle, disperse the debris cloud, and spread the energy before it reaches the most important parts of the vehicle. Sometimes, the most effective protection is not a thicker layer of material, but the empty space placed in exactly the right position between two walls. A thin layer of metal sits on the outside of the spacecraft, directly facing the stream of dust and debris rushing toward it. Behind this layer is not a thick block of steel, but a gap that appears completely useless. Only farther inside lies the main wall protecting the instruments, fuel, or pressurized compartment. At first, this arrangement seems counterintuitive. When people need to defend against a fast-moving object, they usually imagine making the wall thicker, harder, and heavier. Yet, in a hypervelocity impact, a single solid barrier is not always the most effective solution. When a dust particle strikes the surface, the danger comes not only from its mass, but also from how tightly its energy is concentrated. If all of that energy enters one small point, the material may be penetrated deeply before the force has time to spread into the surrounding area. A good shield must therefore do more than simply try to stop the particle. It must break the particle apart, disrupt its original shape, and provide enough distance for the energy to spread before reaching the spacecraft's main wall. This principle lies behind one of the most important protective structures in modern space engineering, commonly known as the Whipple shield. The name comes from the American astronomer Fred Whipple, who proposed using a thin, protective layer positioned some distance away from the spacecraft's hull. The outer layer does not need to be thick enough to stop the object completely. Its first purpose is to change the object's state before it reaches the more important structure behind it. This outer layer is often called the bumper. It may be made from aluminum or another lightweight material that does not add too much mass to the spacecraft. When a particle strikes the bumper at high speed, it is crushed, melted, or partly vaporized along with material from the point of contact. What happens after that first collision is the most important part. Instead of a solid projectile continuing directly toward the spacecraft, a cloud forms behind the bumper, made of fragments, droplets of molten metal, vapor, and particles far smaller than the original object. This cloud still carries nearly all the energy of the impact. However, that energy is no longer concentrated along a narrow path. As the fragments travel through the gap between the bumper and the rear wall, they continue spreading apart in many directions. The cloud's cross-section grows wider, distributing the energy across a larger area by the time it reaches the next layer. If the spacing is appropriate, the rear wall no longer faces a solid particle concentrating all of its kinetic energy into one point. Instead, it receives a broader load made up of many smaller fragments that have lost some of their cohesion. While part of the energy has already been converted into heat, deformation, and the expansion of the cloud, the rear wall may still be dented, heated, or stripped of some material. Yet the risk of a direct puncture can be reduced significantly. The empty space between the two layers is therefore not wasted space, but a region where the impact is allowed to expand and gradually lose its concentration. If the bumper and the main wall are placed too close together, the debris cloud does not have enough time to spread. The fragments remain concentrated within a small area and may continue behaving much like the original object. In that case, the outer layer merely breaks the particle into pieces without reducing the danger to the rear wall enough. If the two layers are placed farther apart, the cloud can spread across a wider area before reaching the main wall. However, the distance cannot be increased indefinitely. A structure that is too wide makes the spacecraft bulky, more difficult to launch, harder to stabilize, and exposes a larger surface area to possible impacts. Every centimeter of empty space must be supported by a structural frame. Braces, joints, and surrounding layers all add mass. In space, the gap itself weighs nothing, but the structure required to preserve that gap has real mass and must be accelerated along with the rest of the spacecraft. A simple Whipple shield may consist of only one bumper, an empty gap, and a rear wall. More advanced versions add several layers of material to break the particle apart more effectively, capture smaller fragments, and absorb the remaining energy before it reaches the pressurized compartment. Some configurations use layers of heat-resistant ceramic fabric, which can further break up and disperse hot metal fragments. High-strength fiber layers such as Kevlar can trap fragments that have already slowed down, preventing them from traveling deeper into the structure. Each layer performs a different role in weakening the impact. The first bumper breaks apart the particle and creates the debris cloud. The gap allows that cloud to expand. The ceramic layer further crushes the larger remaining fragments, while the fiber layer absorbs their motion and captures the material that remains. The pressure wall behind them is exposed only to the portion of energy that has already been dispersed through several stages. The International Space Station uses several forms of protective structures based on this principle. Shielding is not identical everywhere, because the risk of impact varies with direction, location, and the type of equipment behind each surface. Habitable modules require a different level of protection from areas containing less critical equipment. Some surfaces may use a basic Whipple shield, while higher-risk areas require reinforced multi-layer versions. The goal is not to make the entire station impossible to penetrate, but to reduce the probability that a small particle will breach the pressure wall as much as possible throughout the station's operational life. To test these structures, NASA uses hypervelocity impact laboratories. In one experiment representing the shielding of an ISS module, an aluminum sphere about 10 millimeters in diameter and weighing nearly 1.5 grams was fired at roughly 5.67 kilometers per second. An object 1 centimeter wide does not seem large when placed on a desk. Yet, at nearly 6 kilometers per second, it carries enough kinetic energy to cause severe damage if it strikes a spacecraft wall directly. The experiment was designed not only to determine whether the sphere would penetrate, but also to observe how the entire object dispersed during impact. High-speed cameras recorded the instant the sphere struck the outer layer and transformed into an expanding cloud of debris. After the test, engineers examined every layer to determine how much material had been lost, how widely the debris had spread, and whether the pressure wall behind it had remained intact. A shield is considered effective when the main wall shows no complete penetration or dangerous cracking. However, the results must also account for material breaking away from the rear surface, structural deformation, and the possibility that smaller fragments may still enter the area containing equipment. These tests allow engineers to adjust the thickness of the bumper, the spacing between layers, and the type of intermediate material. Changing the gap by only a few centimeters or adding a suitable fabric layer can significantly alter the damage experienced by the rear wall. This shows that a Whipple shield does not work through hardness alone. It works by controlling the sequence of the collision. The incoming object is forced to break apart at a location prepared for that purpose, after which the fragments are directed through a gap long enough for them to spread before reaching the final protective layer. However, a structure that works well in Earth orbit may not remain equally effective when velocity increases by thousands of times. Modern Whipple shields were developed for micrometeoroids and orbital debris, typically moving at speeds ranging from several to several tens of kilometers per second. No laboratory has ever fired a macroscopic dust particle into a shield at 60,000 kilometers per second. The difference between test velocities and 20% of the speed of light is far too great to assume that every process will simply increase by the same proportion. At interstellar speeds, the dust particle may become almost completely ionized the moment it strikes the first layer. Plasma, secondary radiation, and high-energy particles may travel deeply into the material through mechanisms that are not entirely like the debris clouds seen in present-day experiments. The bumper may break apart the particle, but it may also create a stream of extremely hot plasma moving into the gap behind it. The empty space can still help this material expand, yet the rear wall must now endure electrical charge, radiation, and far greater heat than traditional Whipple shields were designed to handle. A protective structure used on the ISS cannot simply be scaled down or transferred unchanged to an interstellar spacecraft. The International Space Station has a mass of hundreds of tons, a large surface area, and support from a logistics system close to Earth. In some cases, its components can be inspected, replaced, or repaired. An ultralight interstellar probe, by contrast, must carry everything it needs from the beginning. If it weighs only a few grams, adding multiple bumper layers, gaps tens of centimeters wide, and protective fiber sheets could increase its total mass many times over. Greater mass requires more energy to reach 20% of the speed of light. The laser system would need to operate at greater power or for a longer period. The sail would have to withstand heavier loads, and the entire structure would need to be redesigned. For a gram-scale spacecraft, even adding a few millimeters of shielding could significantly change the challenge of acceleration. The spacing between layers also creates a challenge involving the spacecraft's shape. A longer vehicle can provide enough room for the debris cloud to expand, but an elongated structure is more vulnerable to drifting out of alignment during the journey. If the protected face no longer points precisely in the direction of travel, the thinner side surfaces may become exposed to the stream of interstellar dust. Spacecraft, driven by light sails, face a different limitation. During acceleration, they need a very large sail to receive force from the laser beam. Once the desired velocity has been reached, that large area becomes an exposed surface, vulnerable to dust impacts unless it can be folded, detached, or rotated into a safer position. A protective structure suitable for a crewed spacecraft would not necessarily work for a light sail. A large vehicle can carry thick shielding, backup compartments, and repair robots. But it is far more difficult to accelerate to relativistic speeds. An ultralight probe is easier to accelerate, yet it has almost no room for complex protective systems. Even when the shield successfully prevents a particle from penetrating the main wall, the danger has not completely disappeared. Secondary fragments may travel away from the expected path and pass through joints, shield edges, or areas that the protective structure cannot cover entirely. A small piece of metal may not be capable of penetrating a pressure wall, yet it could still sever an electrical wire near the surface. A hot fragment could puncture a coolant line, allowing fluid to escape and causing the heat rejection system to stop working. A collision that destroys only one electronic chip may still determine the fate of a small probe. When all navigation, imaging, or communication capabilities depend on only a few components, the outer shell does not need to be completely destroyed for the mission to end. The design must therefore account for paths that bypass the main shield. Electrical wiring may need to be placed deeper inside, divided into several independent routes, or protected by separate materials. Critical pipes may need to be duplicated so that a single puncture does not disable the entire system. Sensitive equipment should also not be positioned directly behind the area most likely to experience an impact. The gap between the bumper and the main wall allows the debris cloud to expand, while additional distance between the main wall and the equipment gives heat, pressure, and material even more time to disperse. A well-protected spacecraft needs more than a strong shield. It also requires an internal arrangement that makes it difficult for damage to spread from the surface into the entire system. Critical components must be hidden behind multiple layers, separated from one another, and able to continue operating when one region is lost. Yet every backup layer increases mass, size, and complexity. When a spacecraft must travel for decades without maintenance, more components also mean more possible points of failure from aging, radiation, or thermal stress. There is no single configuration suitable for every mission. A gram-scale probe making a high-speed flyby of Alpha Centauri may accept a high level of risk and rely on launching many spacecraft at once. A large vessel carrying human beings would have to prioritize thick shielding, multiple compartments, and the ability to make repairs. The Whipple shield is therefore not the final answer to the entire problem of interstellar dust. It is an important principle showing that controlling the flow of energy can be more effective than simply making a wall thicker. Its greatest value lies in forcing the collision to unfold in a less dangerous sequence. The dust particle strikes the outer layer, breaks apart, and expands into a cloud. The empty gap reduces the concentration of the fragments. The layers behind it continue absorbing the remaining energy before it can reach the region that must be protected. The seemingly empty space between two walls therefore acts almost like a component of the shield itself. It does not stop the object through mechanical strength, but gives it enough distance to lose the concentrated shape that makes it dangerous. Even so, the space behind the wall does not always contain only a small instrument that can be wrapped in additional protection. In a crewed spacecraft, behind that wall lies an environment filled with air, water, wiring, and systems that must operate continuously to sustain life. When the shield is no longer protecting a single camera or processor, but an entire pressurized room, the consequences of a small puncture change completely. In that case, what is trying to escape is not only heat or debris, but the entire atmosphere that human beings need in order to remain alive. Outside, the spacecraft lies the cold vacuum, with almost no pressure at all. Inside are air, water, people, electrical equipment, and thousands of pipes that must operate continuously. Between these two completely different environments, there may be nothing more than a metal wall, only a few centimeters thick. That wall does more than give the spacecraft its shape. It keeps every molecule of air inside, prevents heat from escaping too quickly, and protects every system from the space environment. When a dust particle penetrates it, the result is not merely a scar in the metal, but a direct passage connecting an occupied room to the emptiness outside. However, the danger posed by a puncture cannot be judged by diameter alone. A small hole in a less critical area may be detected and repaired, while a similar tear in a fuel tank, module hatch, or coolant line could trigger a far more serious chain of failures. Before considering a crewed spacecraft, it is important to distinguish it from the tiny probes that might be sent toward nearby stars. A vehicle weighing only a few grams may carry no pressurized compartment, contain no air, and require no life support system. Even so, that does not make it immune to an impact. Inside a spacecraft smaller than the palm of a hand, the camera, control chip, memory, orientation sensors, power source, and communication system must all be placed very close together. There are few layers of material to stop fragments from traveling deeper, and almost no room to separate critical components from the forward surface. If a dust particle strikes a sacrificial shield designed to absorb damage, the spacecraft may continue its journey. But if the impact lands only a few millimeters away and hits the camera, the entire ability to observe the destination star system may disappear. The rest of the spacecraft may keep flying, but it will no longer collect the data people have been waiting for. An impact on the control chip could leave the probe unable to process information or maintain the correct orientation. If the memory is damaged, images already recorded may vanish before they can be transmitted home. If the antenna or laser transmitter stops working, the spacecraft may reach its destination with no way to tell Earth what it has seen. A probe, therefore, does not need to be torn into pieces to be considered lost. The failure of a single function without a backup could end a mission lasting decades within a few millionths of a second. Mechanically, the spacecraft may still exist, but scientifically, it has fallen silent. A crewed spacecraft faces a different kind of vulnerability. It may be larger, carry more layers of shielding, and have enough space for backup systems, but the number of components requiring protection also increases enormously. Every life support system creates another path through which damage can spread. The air-filled compartment is the most obvious concern, but it is not the only place where a disaster could begin. Inside the hull are fuel tanks, oxidizer tanks, water lines, electrical systems, batteries, data cables, and cooling circuits. External radiators must connect to internal pipes to carry heat away from the spacecraft. Windows create additional regions of transparent material that cannot be as thick as a solid block of metal. Hatches connecting separate modules must remain airtight while still being able to open and close throughout the journey. These transition points are more complex than a continuous wall and may become vulnerable if an impact occurs in exactly the wrong place. Life support equipment is not contained inside a single box. Air must circulate, carbon dioxide must be removed, and oxygen must be replenished. Water is routed through many areas for drinking, hygiene, and cooling. A puncture that does not strike the living compartment directly may still disable a system required to keep that compartment habitable. For this reason, NASA and other space agencies do not focus only on whether a particle penetrates a metal panel. Tests also measure the size of the hole, the length of surrounding cracks, the deformation of pressure vessels, and the strength that remains after impact. A structure may avoid complete penetration and still become too weak to remain safe. At the point of impact, the metal may be pushed inward and stretched around the crater. If the stress spreads across a wider region, a crack may begin at the impact site and continue growing while the vessel remains under internal pressure. The original hole may be only a few millimeters wide, yet the cracks surrounding it may become the greater danger. The pressure inside is always pushing the spacecraft's walls outward. When the structure is intact, that force is distributed evenly across the hull. After an impact, the region of metal that has been thinned, heated, or deformed must continue bearing the same pressure, allowing the damage to grow even long after the dust particle itself has disappeared. The inner surface of the metal may also break apart under the shock wave. Small fragments flying into the compartment could sever wires, damage equipment, or create additional punctures in pipes. In that case, a single impact on the outer hull could produce several failures inside without the original object ever passing completely through. Insulation behind the wall may be torn or scorched. If it loses its protective ability, a small region of the compartment will begin exchanging heat with the outside differently than before. Over a long journey, that seemingly local change could create cold spots, cause water vapor to condense, or force nearby equipment to operate beyond its design limits. If the dust particle strikes a coolant line, fluid may escape through the small opening and freeze almost immediately. The heat rejection system would then lose pressure, preventing heat from computers, power systems, and living spaces from being carried away efficiently. The spacecraft may be surrounded by the cold of space and still become dangerously hot inside. An impact on the electrical system could also produce consequences that are difficult to predict. A small metal fragment might connect two conductors that were meant to remain isolated, creating a short circuit or an electrical arc. In an oxygen-rich environment, a tiny spark could become more dangerous than the puncture that created it. Fuel and oxidizer tanks carry a different set of risks. A small hole could cause a slow leak, gradually depriving the spacecraft of its ability to adjust course over the following months. If two reactive substances meet outside a controlled location, the consequences could be far more severe, even though the original impact caused only minor damage. Not every puncture in a pressurized compartment causes all the air to escape immediately. The rate of decompression depends on the size of the opening, the initial pressure, the volume of the compartment, and whether the damaged area can be isolated. A small hole may produce only a faint hiss and lower the pressure slowly enough for the crew to respond. Inside a large compartment, air escaping through an opening only a few millimeters wide would not pull everything outside, as it often does in movies. The gas would flow out gradually, while larger objects would remain in place unless they were very close to the opening. The greater danger is the limited time available before the pressure falls below a safe level. A long tier creates a very different situation. Its larger opening allows pressure to drop more quickly, while the surrounding structure may continue being pulled apart. If the damage lies near a hatch or a load-bearing joint, sealing the compartment or applying a patch becomes even more difficult. The incident may begin with a change too subtle for anyone to notice. Pressure sensors detect a gradual decline and send the data to the central computer. The system compares readings from several compartments to determine which area is losing air faster than normal. If the leak exceeds a safe threshold, an alarm is triggered and airtight doors between modules can be closed. Dividing the spacecraft into multiple compartments prevents all of its air from escaping through a single opening. One section of the structure may be lost, while the remaining areas continue to hold pressure. The crew must leave the suspected area before the doors close completely. In those moments, they must do more than move themselves to safety. They also need to ensure that airflow, electrical power, and control systems are shifted into a new configuration. An airtight door may preserve the atmosphere, but it can also sever many connections between modules. Once the area has been isolated, robots or crew members must locate the exact source of the leak. A hole only a few millimeters wide can be extremely difficult to find on a large wall, especially when insulation, equipment cabinets, and wiring conceal the inner surface. Ultrasonic sensors or airflow detectors can help narrow the search. Air escaping through a small opening may produce a faint hiss, but spacecraft compartments are usually filled with the constant sounds of fans, pumps, and other equipment. In that continuous background noise, the sound is not easy to distinguish. The crew may use handheld sensors, or observe the movement of lightweight materials to determine the direction of the airflow. Once the puncture is found, a temporary patch can be applied from the inside. The pressure within the compartment pushes the patch against the surface, helping it seal more firmly when properly designed. A stronger repair can then be installed to restore air tightness and redistribute the load around the damaged region. Sealing the opening, however, does not mean the structure has returned to its original condition. The metal around the impact site may be cracked, thinned, or weakened. Engineers aboard the spacecraft must determine whether the compartment can continue holding pressure for years or should be used only under restricted conditions. If the risk is too high, the module may have to remain permanently isolated. The spacecraft would then continue its journey with less living space, storage capacity, and equipment. Any resources that can still be used must be transferred to a safe area before the final door is closed. Electrical power must also be rerouted if cables pass through the lost module. The cooling system must find another path to carry heat toward the radiators. Even an uninhabitable compartment may still contain wiring, pumps, or equipment on which the rest of the spacecraft depends. On a flight lasting only a few days, losing one module would already be a serious problem. On an interstellar journey lasting decades, it could completely reshape life for the crew. Personal space would shrink, supplies would become more limited, and the remaining systems would have to operate under heavier loads for much longer than originally planned. A small puncture may therefore not kill the spacecraft immediately, yet it can reduce the safety margin for every remaining year of the journey. Once a backup system has been used to replace something that failed, the spacecraft no longer has that second layer of protection against the next emergency. A journey through the interstellar medium will not involve only one collision. After the shielding has been damaged, that region may become easier to penetrate if it encounters another dust particle. Small cracks may also grow under repeated changes in temperature, pressure, and structural load. A crewed spacecraft therefore needs more than thick material. It must have independent compartments, airtight doors, leak detection sensors, redundant power routes, and the ability to perform repairs from within. Critical systems cannot depend on a single pipe or cable running through the entire structure. Yet every redundant system makes the spacecraft heavier and more complex. Adding a reserve oxygen tank, a second cooling loop, or another layer of hull increases the energy required for acceleration. When the goal is to reach a significant fraction of the speed of light, protective mass becomes part of the journey's central challenge. An ultralight probe solves the mass problem by removing almost everything that is not essential. In return, it becomes extremely vulnerable to an impact at exactly the wrong location. A crewed vessel can carry repair capabilities and backup systems, but its enormous mass makes reaching interstellar speeds far more difficult. There is no single hole size that marks the boundary between safety and disaster. A 1 mm opening in the outer shield may have little consequence, while damage of the same size in a coolant line or central control circuit could disable a critical system. The location, shape, and surroundings of the puncture all matter. A round opening with stable edges may be easier to repair than a long crack. Damage on a flat, accessible surface is very different from a puncture hidden behind an equipment cabinet or located at the junction between two modules. The speed of the response can also determine the outcome. Early detection allows doors to close, while most of the air is still inside. If the hole lies in an unmonitored area or the warning system fails, the spacecraft may lose significant resources before the crew understands what is happening. A major impact usually produces unmistakable signs. Pressure falls rapidly, vibration sensors detect the impulse, and several alarms appear at once. The crew knows that a serious event has occurred and immediately shifts into emergency procedures. But the danger during a long journey will not always arrive in such an obvious way. A small particle may only scratch a window, erode a coating, or create a dent that is not yet deep enough to cause a leak. No alarm sounds, and the spacecraft continues operating as though its surface has not changed. Later, another particle strikes nearby. More small impacts follow over the years. No single collision is powerful enough to threaten the flight, yet together they gradually thin the shielding, reduce the clarity of the windows, and create more weak points in the material. A spacecraft may survive every individual event and still decline through accumulation. It may lose no air, suffer no explosion, and remain perfectly on course. Yet its ability to observe, generate power, and release heat may diminish so slowly that the change is almost impossible to notice from one day to the next. Each scratch may be too small to stop the flight. After many years, however, their combined effect can change how the spacecraft sees ahead, gathers energy, and releases heat into the darkness. Destruction would then come not from a single puncture, but from millions of tiny marks, sharing a surface that never has the chance to be replaced. After 20 years of traveling through the darkness between the stars, the glass panel at the front of the spacecraft still holds its original shape. No large crack runs across its surface. No opening is wide enough to be seen from a distance, and there is no sign that it has ever endured a single catastrophic impact. Yet the glass is no longer as transparent as it was on the day the spacecraft left the solar system. Countless pits smaller than the width of a human hair now cover the surface. Each one blocks or deflects only a tiny fraction of the incoming light, but when millions of these marks exist together, they form a haze that can never truly be cleaned away. Light from the star ahead still enters the instrument, but the image is no longer as sharp as the original design intended. A large collision is usually easy to notice because it leaves a deep crater, sends vibrations through the spacecraft, or triggers an alarm. Long-term erosion is far quieter. There is no single moment that marks the failure, because the spacecraft loses only an almost insignificant amount of material each day. This creates a different question from the threat posed by a rare, unusually large dust grain. The spacecraft may survive every individual collision, remain on course, and never be fully penetrated, but could the total number of impacts over several decades still be enough to cause the mission to fail? The most vulnerable components are often the surfaces that must remain directly exposed to space. Windows, lenses, optical mirrors, star trackers, navigation cameras, radiators, solar panels, antennas, light sails, and thermal control coatings must all leave at least part of themselves uncovered in order to perform their functions. A camera cannot be placed entirely behind thick metal and still be allowed to observe the sky. A radiator cannot be sealed beneath insulation and still release heat into space. These components must be protected, yet they must also continue to see, collect energy, transmit signals, or exchange heat with their surroundings. A micrometer-sized dust grain may create only a tiny crater in glass. On its own, that mark has almost no effect on the image. Enough light still passes through the undamaged surface for the camera to function, and the computer can process a small amount of noise without difficulty. But an optical surface is not judged by a single point. It must preserve its transparency, shape, and ability to transmit light across the entire usable area. As the number of pits increases, more light begins scattering in different directions instead of converging precisely on the sensor. A star that once appeared as a compact point of light may spread into a wider blur. Faint objects close to a bright source become easier to hide, while measurements of stellar positions grow less precise. The camera still works, but its ability to distinguish fine detail gradually declines as the erosion continues. For a star tracker, even a small error can affect the spacecraft's ability to determine its orientation. The instrument observes patterns of stars and compares them with a map stored in memory to determine where the spacecraft is pointing. If the images become blurred or filled with too many false points of light, recognition may become slower and less accurate. A spacecraft flying past Alpha Centauri would not have much time to correct its mistakes. At a significant fraction of the speed of light, it could cross the most important observation region in only a few hours or days, depending on the target and the mission design. Every measurement must be made while the spacecraft continues rushing forward, unable to turn back. If the glass has deteriorated after 20 years, the camera may arrive at the right place, but no longer be sensitive enough to record faint targets. A small planet close to a bright star could disappear inside the scattered glow. Details on the surface of a distant world might become no more than a few patches of color with little scientific value. Optical mirrors face a similar danger, even though light does not need to pass through them. A well-functioning mirror must reflect light in a very precise direction. Tiny craters alter the local reflection angle, causing part of the light to scatter away from its intended path. The coating on a mirror may be only a tiny fraction of a millimeter thick. It is selected to reflect particular wavelengths, but that thinness also makes it vulnerable to being scratched, stripped away, or altered by dust impacts. As small sections of the coating disappear, the mirror collects less light even when the underlying surface remains intact. This damage does not necessarily increase at a steady rate. At first, a small number of pits makes almost no difference. Once the density of damage passes a certain level, the scattered regions begin to overlap, and image quality declines more rapidly. The spacecraft may operate normally for many years, then lose noticeable precision near the end of the journey. Cameras and telescopes are not the only instruments that can slowly die in this way. Solar panels also depend on large surface areas to collect energy, and each region contributes only a small part of the total output. A single impact usually destroys only a tiny area, but accumulated damage can gradually reduce power production. A solar panel is made from many semiconductor cells connected by thin electrical conductors. A dust particle may damage the semiconductor at the point of impact, strip away a protective coating, or sever one of those conductors. If the damage is limited to a single cell, the rest of the panel may continue supplying power. However, some conductors connect many cells within the same string. If one of them is broken, the area that stops functioning may be much larger than the crater itself. A small scratch on the surface can therefore reduce the output of an entire group of cells behind it. Metal fragments or plasma produced during the impact may also create an unintended connection between regions at different electrical potentials. Under certain conditions, this can cause a short circuit or an electrical arc. The damage may then spread beyond the area struck by the particle and travel through the electrical network into surrounding regions. Repeated small impacts also weaken protective coatings. The material underneath becomes more directly exposed to radiation, temperature changes, and charged particles. A solar panel does not lose all of its power in a single day, but each year it may provide slightly less energy than it did the year before. Even so, solar panels are useful only while the spacecraft remains relatively close to a star. Light intensity falls rapidly with distance. In the far reaches beyond the solar system, the same broad panel would collect far less energy than it would near Earth. An interstellar spacecraft may therefore need to rely on stored batteries, radioisotope power sources, a small reactor, or another form of energy. Every option brings its own mass, lifespan limitations, and cooling requirements. Even when solar panels are no longer the primary power source, erosion can still affect nearby sensors or coatings. Radiators face an even deeper paradox. Space is extremely cold, but a vacuum cannot carry heat away through convection as air does inside a room. The spacecraft can release most of its excess heat only by radiating it from surfaces specifically designed for that purpose. To reject large amounts of heat, radiators need broad surface areas and must face open space. Those surfaces cannot be covered with thick armor, because the protective layer would interfere with heat radiation. The more area the spacecraft exposes to improve cooling, the greater the probability that a dust particle will strike it. A very small puncture can have serious consequences if the radiator uses liquid coolant circulating through narrow tubes. The coolant may leak into space, reducing pressure throughout the entire loop. If circulation stops, heat from computers, power systems, and living compartments can no longer be transferred efficiently to the radiator. The spacecraft may then grow steadily hotter even while traveling through an extremely cold region of space. Heat does not disappear simply because the surrounding environment is cold, because there is no air between the equipment and the vacuum to carry it away. If the radiator weakens, heat accumulating inside may force components beyond their safe operating limits. Even without a puncture, the radiator surface can still be altered by countless tiny craters. Its ability to emit thermal radiation depends on the material, surface texture, and coating. As the surface is heated, stripped away, or covered by material that melts and solidifies again after impacts, its thermal properties no longer match the original design. A darkened region may absorb and emit heat differently from an undamaged one. A coating designed to reflect starlight while radiating efficiently at infrared wavelengths may gradually lose that ability as dust particles break it apart. Temperature across the radiator then becomes uneven, creating additional stress and allowing older cracks to grow. This process may unfold so slowly that the control system can compensate for a long time. The computer can reduce power to certain instruments, redirect coolant toward the sections that still work, or change the spacecraft's orientation so the radiator faces a more favorable region of space. Yet every adjustment consumes reserves that are ultimately limited. As the effective radiator area decreases, the spacecraft must decide which instruments can remain active. The camera may be turned on only briefly. The transmitter may have to operate at lower power, or the computer may process data more slowly to reduce the amount of heat it produces. As the spacecraft approaches its destination star, demand rises again at exactly the moment when its systems have grown old. Cameras, sensors, and computers must operate continuously to collect data during the brief flyby. A weakened radiator may force the spacecraft to shut down some instruments just when they are needed most. Light sails are also among the structures most vulnerable to erosion. To receive thrust from a laser beam, a sail must be extremely broad yet exceptionally light. It may be so thin that a single dust particle creates a hole many times greater than the thickness of the sail itself. During acceleration, the sail must preserve both its shape and its precise reflective angle. Small holes change the way light pressure is distributed across the surface, creating uneven forces. If one side suffers more damage than the other, the spacecraft may begin to rotate or drift away from the center of the laser beam. Some designs assume that the sail will be detached, rolled up, or turned aside once acceleration is complete. Others may use it as a large antenna for transmitting signals. Each choice changes how the sail is exposed to the stream of dust during the rest of the journey. If its broad surface remains facing the direction of travel, the number of particles it sweeps through rises dramatically. A sail covering many square meters encounters far more material than a spacecraft body only a few centimeters wide. Even if each particle is extremely small, the total number of impacts can quickly turn the thin surface into a sheet filled with holes. If the sail is rotated so that it lies parallel to the direction of motion, its frontal area becomes smaller, but its thin edge must then endure the full stream of impacts. Even a slight error in orientation over many years could gradually expose more of the sail's broad surface to the interstellar environment. Antennas face a similar challenge. To send a weak signal back to Earth across several light years, the spacecraft must focus its energy into a very narrow beam. The transmitting or reflecting surface must preserve its shape with enough precision to prevent the signal from spreading too widely. Small dents in the antenna can alter the direction in which individual regions transmit energy. Each error may be almost insignificant on its own, but together they make the beam less focused. Less energy then reaches Earth, even though the transmitter aboard the spacecraft continues to operate normally. For a communications link that is already extraordinarily weak, even a modest loss of efficiency may be enough for the signal to disappear into the noise. The spacecraft may have collected the data, its memory may remain intact, and its transmitter may still be operating, yet the photons carrying the information are no longer focused tightly enough for telescopes on Earth to detect them. Thermal control coatings on the spacecraft's body are also affected by repeated impacts. Some surfaces are designed to reflect light, while others absorb or release heat at different rates. This balance helps the spacecraft maintain a stable temperature without consuming too much energy. When the coating is scratched away, the underlying material becomes exposed and responds differently to radiation. One side of the spacecraft may grow warmer than the other, creating tiny but persistent distortions. Orientation sensors must make continuous corrections, while the structure undergoes additional cycles of expansion and contraction. The leading edge of the spacecraft experiences the greatest erosion because it sweeps directly through the interstellar medium. The sacrificial material placed there is designed to wear away gradually during the journey. However, the rate of material loss depends on the actual density of gas and dust, which cannot be known precisely along every part of the route. If the environment is thinner than predicted, the spacecraft may reach its destination with much of the shield still intact. If it passes through a dustier region, the protective layer may erode too soon. The layers behind it would then begin receiving direct impacts during the final years of the journey. A shield does not fail in a single instant. It may continue working after losing part of its thickness, but its ability to absorb energy gradually declines. Each later particle encounters less material before reaching the equipment deeper inside. Impact craters can also overlap. A new particle striking an older crater passes through a region that has already been thinned and deformed. The probability of any one overlap may be low, but after millions of impacts, some particles will almost certainly strike areas that have already been damaged. Throughout the same period, the material must also withstand thermal cycles, radiation, and structural stress. A microscopic crack that is harmless when it first appears may grow over many years. Dust is not the only cause of structural aging, but it creates additional starting points from which weakening can spread. Cumulative erosion is therefore not simply the sum of the depths of individual craters. It also changes the shape, optical properties, electrical conductivity, heat radiating ability, and strength of the surface. Each function declines in a different way, making the lifetime of the entire spacecraft difficult to predict. A system may continue operating below its original design performance. The camera may lose resolution but still recognize a star. The power system may lose some output, yet still provide enough energy to keep the computer running in a low power mode. The radiator may become less efficient, but remain safe as long as several instruments are not operated at the same time. The problem emerges when many small losses begin interacting. Because the window has grown cloudy, the camera needs longer exposures, forcing the computer to process more data. The computer must operate longer and produces more heat, while the radiator has already weakened and the power system can no longer provide as much energy as before. Each individual system may still remain within its operating limits, yet the spacecraft as a whole no longer has enough margin to perform the mission at its original level. A small temperature change, a memory error, or one final impact could push several components beyond their limits at the same time. This is how a spacecraft can die without experiencing any clear moment of destruction. It does not explode, lose contact immediately after a collision, or develop a large hole in its hull. Its ability to perform the mission simply declines until one essential function is no longer strong enough to be useful. The spacecraft may reach Alpha Centauri with its structure still almost intact. It may retain its velocity, continue rotating on command, and still have electrical power. Yet the camera has become blurred, the antenna spreads its signal too widely, the cooling system allows only a few minutes of operation, and the forward shield has nearly been consumed. Physically, the spacecraft has survived the journey. Scientifically, it may no longer be able to observe, store, and transmit the data that gave the mission its purpose. Structural survival is therefore not the same as completing the mission. A rare, large dust grain could end the journey in a single instant. Millions of smaller particles could achieve the same result by removing tiny portions of the spacecraft's capability one at a time. The only difference is whether failure arrives suddenly or unfolds quietly over many years. To understand how severe this erosion might become, we need to know how much gas and dust the spacecraft will actually encounter along the way. The darkness stretching more than 4 light-years between the Sun and the nearest star appears almost completely empty, yet it still contains enough matter to produce a continuous stream of impacts throughout the journey. The spacecraft has traveled so far from the Sun that its light now appears as little more than one slightly brighter star among billions of other points. Ahead, there are no planets, no clouds, and no objects large enough to be seen with the naked eye. The darkness between the stars seems completely empty, yet every second, the spacecraft's leading edge passes through countless invisible atoms. This space is thinner than any vacuum people commonly encounter on Earth, but it is not absolute emptiness. Across its immense volume, there are still hydrogen and helium atoms, free electrons, protons, molecules, and small amounts of heavier elements. Scattered through this extremely diffuse gas are dust grains with widely varying sizes, compositions, and densities. A spacecraft at rest in this environment would feel almost nothing. The atoms are too widely separated to produce any noticeable wind, pressure, or drag. But when the spacecraft moves through them at a significant fraction of the speed of light, that stillness becomes a continuous stream of impacts across its entire nose. The question is no longer whether matter exists between the stars. What matters is how much material the spacecraft must sweep through over a distance of more than 4 light-years, and how profoundly that tiny amount of matter may alter its surface after several decades. Most interstellar matter exists as gas. Hydrogen is the dominant component, followed by a smaller amount of helium. Carbon, oxygen, neon, iron, and many other elements are also present, but together they account for only a small fraction compared with the 2 main components. Hydrogen may exist as neutral atoms, as protons, or within molecules. Free electrons move among them, creating regions of partially ionized gas. This environment is not uniform, because temperature, density, and the degree of ionization can vary considerably from one region to another. Interstellar dust makes up a smaller share of the total mass, but it creates a different kind of danger. A hydrogen atom contains very little matter, while a dust grain can concentrate billions or more atoms within a single structure. Gas, therefore, creates continuous bombardment, while dust produces separate but much more powerful impacts at individual points. Many dust grains are thought to contain silicates, carbon-rich materials, or mixtures of heavier elements. In colder environments, their surfaces may also carry frozen molecules. Other grains may contain metallic material or porous structures formed over long periods in space. Their sizes range from particles smaller than the wavelength of light to rare objects that are much larger. Most interstellar dust lies toward the smaller end of this range, but danger is not determined by numbers alone. Rare, larger particles may contribute significantly to the risk of severe localized damage. In the frame of reference of the interstellar medium, the gas atoms drift only slowly. But from a spacecraft moving at 20% of the speed of light, they appear as a continuous beam of energetic particles striking the nose. The spacecraft's own velocity transforms the quiet gas into a relentless bombardment. A proton, entering the material, does not necessarily stop at the surface. It may penetrate a short distance, colliding with electrons and atomic nuclei within the structure as it gradually loses energy. Along the way, it ionizes the material, alters bonds, and leaves behind a microscopic trail of damage. High-energy electrons behave differently. As they slow down inside the material, they can emit braking radiation in the form of high-energy photons. The shield is therefore not only absorbing incoming particles, but also becoming a site where additional secondary radiation is produced. Heavy ions are rarer than hydrogen and helium, but each carries greater mass and electrical charge. As they pass through a material, they leave denser trails of ionization that can alter its crystalline structure, create defects, and gradually degrade its properties over time. These effects do not create large craters like dust impacts. They are more like continuous irradiation, slowly changing the material at the front of the spacecraft. A single atom causes no meaningful damage, but the enormous number encountered over many years can gradually reduce the surface's strength and stability. Dust produces more visible results. When a silicate or carbon grain strikes the spacecraft's nose, its energy is delivered into a small area, causing material to melt, vaporize, or be ejected from the surface. Each particle leaves a crater, and each crater removes a tiny portion of the shield. If the particle is small enough, the impact affects only the surface layer. If it is larger, the resulting plasma and fragments may travel deeper into the material. The outcome depends on the particle's size, density, impact angle, and whether it strikes an intact part of the shield or lands directly on a region that has already been damaged. Some models of travel at around 20% of the speed of light estimate that interstellar gas could damage a surface layer roughly 1/10 of a millimeter thick, depending on the material and the gas density along the route. This does not mean that the entire layer would be stripped away evenly like a shell. Some of the damage would take the form of ionization, crystal defects, and changes to the material's internal properties. The surface might retain its shape, while its strength, electrical conductivity, or optical behavior had already changed. A transparent layer of glass could lose its clarity before losing a significant amount of thickness. Under some assumptions, dust could cause greater erosion, reaching several tenths of a millimeter across the spacecraft's forward face. For a large vehicle, that may seem insignificant. For a spacecraft only a few millimeters thick, or one carrying an extremely lightweight shield, it could represent a substantial portion of the entire protective structure. These numbers come from physical models, not from data collected by a spacecraft that has completed a journey to Alpha Centauri. No instrument has yet traveled the entire route and counted every gas, atom, and dust grain. Current probes have only begun measuring the environment near the outer boundary of the Sun's influence. Astronomers can estimate gas density by studying light from distant stars. As starlight passes through the interstellar medium, atoms and molecules absorb characteristic wavelengths. From these absorption lines, researchers can infer the composition and amount of matter along the line of sight. Dust also leaves its mark on light. It makes distant stars appear dimmer and redder because shorter wavelengths are generally scattered more strongly. However, these observations mainly provide average values across extremely long distances, not a precise map of every region a small spacecraft would pass through. Average gas density is therefore better understood than the abundance of rare, large dust grains. gas particles are numerous enough for their average effects to be measured. Larger grains are much more sparsely distributed, making their exact frequency far more difficult to determine. If a particular type of particle is extremely rare, telescopes and dust detectors may need to observe for a long time before collecting enough examples. A small number of measurements may not represent the entire environment. The route to a specific star may also pass through regions unlike those that have been directly studied. This uncertainty makes shield design especially difficult. Most of the journey may contain only small particles that cause slow erosion, yet a grain thousands of times larger than average, however rare, could still deliver enough energy to cause deep damage. Engineers cannot design only for the most common particle, because the spacecraft must also have some chance of surviving rare events. But if they try to protect it against every imaginable particle size, the shielding becomes so heavy that the spacecraft can no longer reach the required velocity. Interstellar space is not perfectly uniform in density. The spacecraft may travel through thin regions containing very few atoms per unit volume, then enter denser gas where the rate of bombardment against its nose increases for a time. The boundaries between these regions may not be as clear as the edge of a cloud on Earth. Density may rise gradually across an enormous distance. The spacecraft would not see a wall of matter ahead, but its sensors might record a slow increase in particle impacts and heat along the shield. The ratio of dust to gas may also change. One region may contain relatively abundant hydrogen but few solid particles, while another may hold more dust than average. The composition of that dust also depends on the history of the material, including generations of stars that formed, aged, and released elements into space. Some grains may be porous and break apart easily on impact. Others may be denser and contain more silicate or metal, allowing them to deliver energy in a more concentrated way. Two particles with the same diameter but different densities can have significantly different masses and kinetic energies. The environment may also contain variations that have not yet been fully mapped. Shock waves from ancient events, the movement of interstellar clouds, or the influence of stellar winds may create structures too small to be easily resolved through remote observations. A route chosen because of its low average density could still cross a localized region containing more dust. Across such an enormous distance, even a small error in direction could carry the spacecraft through an environment different from the one originally predicted. To understand how much material the spacecraft will encounter, we need to consider its frontal area. As the vehicle moves forward, it sweeps through an imaginary cylinder in space. The volume of that cylinder depends on the distance traveled and the area of the spacecraft facing the direction of motion. A spacecraft with a frontal area of 1 square centimeter sweeps through far less space than one with a frontal area of 100 square meters. The particle density may be the same, but the larger spacecraft blocks a wider region, so the total number of impacts increases accordingly. This is one advantage of a gram-scale probe. If the spacecraft is made extremely small and oriented so that its narrowest cross-section faces forward, the probability of encountering a rare, large dust grain is reduced. An object must lie directly within that very narrow corridor to strike the spacecraft. However, a small probe has little material available to absorb an impact. A particle that would leave only a minor dent in a large spacecraft could damage a significant portion of a gram-scale vehicle. A smaller cross-section reduces the number of encounters, but it does not make each collision less severe. A crewed spacecraft faces the opposite situation. A frontal area measuring tens or hundreds of square meters causes it to sweep through far more space. Over the same journey, it is likely to encounter more particles than a small probe in direct proportion to its area. In return, a larger spacecraft can carry thicker shielding, multiple compartments, and redundant systems. A dust particle striking a non-critical region may remove only a small amount of material. A damaged instrument may be replaced, while a punctured compartment can be isolated from the rest of the vehicle. The ability to make repairs changes how the risk is evaluated. A gram-scale probe must avoid or survive impacts through its original design because it has almost no ability to replace its own components. A larger spacecraft may tolerate a certain amount of damage if it carries enough material and robotic systems to perform repairs during the journey. But shielding, backup compartments, and repair equipment all add mass. Accelerating a large spacecraft to 20% of the speed of light would require energy far beyond the capabilities of any propulsion system currently in operation. Every additional ton of protection makes an already difficult problem even more remote. A long, narrow spacecraft could reduce its frontal area while preserving a large internal volume. Its compartments could be arranged one behind another beneath a thick forward shield, placing most equipment within the protective shadow of the first layer. This structure would sweep through less of the interstellar medium than a spacecraft with a broad forward face. However, the spacecraft would have to maintain an extremely precise orientation for several decades. If it rotated out of alignment, its long side or lateral radiators would become exposed to the stream of gas and dust. Even a small attitude error sustained over time could multiply the area being swept through. Accumulated electrical charge, weak magnetic fields, radiation pressure, and uneven impacts could all cause the spacecraft to rotate. Its control system would need to make continuous corrections without consuming too much fuel. Every adjustment would also have to keep the forward shield pointed precisely along the spacecraft's true direction of motion. The swept area also changes if the spacecraft carries a light sail. During acceleration, the sail must be broad enough to receive force from the laser beam. Afterward, if it remains deployed and nearly perpendicular to the flight path, it will sweep through a far greater volume of space than the small spacecraft body behind it. Rolling, folding, or detaching the sail could reduce the danger, but every moving mechanism would have to function after the intense acceleration phase. A minor failure that prevents the sail from retracting could increase the probability of impact throughout the entire remainder of the journey. Designers must therefore balance the area required for acceleration, the area needed for communication, and the area that must be minimized to avoid dust. The same surface may be useful during one stage of the mission and become a burden during another. There is no single shield thickness that is correct for every spacecraft. The protective layer must be calculated according to the material, velocity, frontal area, travel time, and acceptable level of risk. Most importantly, the calculation also depends on the distribution of dust along the specific route. If the environment is assumed to be too thin, the shield may erode completely before the spacecraft reaches its destination. If too much dust is assumed, the vehicle may carry more protection than necessary and become unable to accelerate to its intended speed. Uncertainty surrounding rare, large particles makes an absolute guarantee impossible. Engineers can calculate a probability of survival, but they cannot prove that the spacecraft will never encounter a particle beyond its design limits. Every interstellar mission must accept some degree of risk that cannot be eliminated. Launching many probes may be one way to address that uncertainty. Each spacecraft would travel through a slightly different corridor, so they would not encounter exactly the same dust particles. Some might be destroyed, while the others continued toward the target. For a crewed spacecraft, a strategy based on numbers is far more difficult to apply. Each vehicle must meet a much higher standard of safety, because failure would threaten human lives rather than merely destroy equipment. This requires thicker shielding, greater redundancy, and possibly a lower cruising speed. The interstellar medium is therefore not a wall of matter preventing humanity from reaching the stars. Its density is extremely low, and most particles are not large enough to destroy a spacecraft immediately. Yet the enormous distance and extraordinary velocity make that small amount of material impossible to ignore. The spacecraft is not facing a dense dust storm. It is rushing through a region that is almost empty, where every individual atom becomes a high-energy particle and every small dust grain becomes a concentrated blow. The danger lies in the total distance traveled, the area swept through, and the speed at which the gap is closing. Without knowing exactly how many large particles lie along a route, no one can specify a shield thickness with complete certainty. A shield that is too thin leaves the spacecraft vulnerable, while one that is too thick makes the vehicle so heavy that its propulsion system can no longer accelerate it effectively. Velocity therefore determines more than how long the spacecraft will take to arrive. It also determines the energy carried by every atom and every dust particle striking the nose. Each additional percentage of the speed of light removes years from the journey, while making the almost empty environment ahead increasingly violent. When the velocity rises from 10 to 20% of the speed of light, the travel time may be reduced by nearly half. At the same time, the impact energy of every particle increases by more than 4 times. The spacecraft reaches the star more quickly, but every piece of matter along the way strikes it with greater force. 2 spacecraft leave the solar system in the same direction, both heading toward a star system more than 4 light-years from Earth. One accelerates to 10% of the speed of light, while the other reaches 20%. From a distance, the difference may seem like nothing more than a number, but in terms of travel time and impact severity, it changes nearly every aspect of the mission's design. Ignoring the time required for acceleration and deceleration, the first spacecraft would need more than 40 years to cross a distance of roughly 4.2 to 4.4 light-years. The second would need just over 20 years. It could arrive nearly 2 decades earlier, while its instruments, power source, and control systems were still less affected by aging. The advantage of greater speed is therefore easy to see. A 20-year mission still falls within a period in which one generation of engineers could design the spacecraft, launch it, and wait for its data to return. A flight lasting more than 40 years could extend beyond the careers of the people who built it, while requiring its equipment to remain stable for twice as long. This is one reason concepts such as breakthrough starshot explore the possibility of accelerating ultralight probes to around 20% of the speed of light. Devices weighing only a few grams could be attached to extremely thin sails and pushed by a powerful laser system positioned near Earth. If they reach the intended velocity, they could arrive in the Alpha Centauri region after a little more than 20 years. However, the probes would not carry enough fuel or propulsion capability to slow down when they arrived. They would simply race through the star system at tremendous speed, using a brief window to take images, make measurements, and transmit their data back to Earth. Higher speed shortens the wait, but it also makes every particle of matter ahead more dangerous. When velocity increases from 10 to 20% of the speed of light, the kinetic energy of the same particle does not merely double. It rises by more than 4 times because energy depends very strongly on velocity. A dust particle striking a spacecraft at 0.1 already carries enough energy to melt or vaporize material at the point of contact. At 0.2, that same particle delivers far more energy into the surface, producing a deeper damaged region, a hotter plasma cloud, and potentially more secondary fragments. The stream of interstellar gas also becomes more violent. Hydrogen, helium, electrons, and ions that are sparsely distributed through space strike the spacecraft's nose with greater energy. Each individual particle remains extremely small, but the total heat and ionization produced within the shield increase significantly. As protons and ions enter the material, they leave microscopic trails of damage and alter its internal structure. Electrons slowing down may produce braking radiation, while collisions with atomic nuclei generate additional secondary radiation. The higher the velocity, the more forms of difficult-to-control energy the shield must withstand. The increase in heat is not limited to a few large impact sites. The spacecraft's forward surface must endure an almost continuous stream of particles throughout the journey. If the vehicle travels twice as fast, it encounters more particles every second, while each one also carries greater energy, causing the rate of heat transfer into the surface to rise sharply. The sacrificial material therefore erodes more quickly in real time. Each impact removes more material, creates a deeper crater, or alters the surrounding region more severely. A shield sufficient for a flight at 0.1 may no longer be suitable when the velocity rises to 0.2. Maintaining the correct orientation also becomes more important. The spacecraft is usually designed so that its smallest and best protected forward surface points directly along the direction of motion. If it rotates out of alignment, its sides, light sail, radiators, or optical instruments may become exposed to the stream of interstellar dust. At a lower speed, a small misalignment would still be dangerous, but its consequences might be more limited. At 20% of the speed of light, the same angular error exposes unprotected surfaces to particles carrying far more energy. The attitude control system must therefore remain precise for decades. At first glance, the faster spacecraft appears to have another advantage. It spends less time traveling through the hazardous environment, so it might seem that the total damage would be lower. However, The same route contains nearly the same amount of gas and dust whether the spacecraft crosses it in 20 years or 40. The spacecraft traveling at 0.2 sweeps through the same column of matter in a shorter period. The number of impacts per second rises, while the energy of each impact is also greater. Passing through the dangerous region more quickly does not automatically make the entire journey safer. If only the number of particles along the same route and the same frontal area are considered, both spacecraft may encounter roughly the same amount of dust. The difference lies in how much energy each particle transfers into the surface. The faster spacecraft does not avoid the material, it simply turns every encounter into a more violent collision. The shorter travel time still provides certain benefits. Electronic equipment experiences fewer years of aging. The power source needs to operate for less time, and the control systems have fewer opportunities to fail through wear. Yet these advantages must be balanced against greater heat, radiation, and impact severity. A slower spacecraft may absorb less energy from each collision, but it must survive for twice as long. Over 40 years, components may degrade, materials undergo more thermal cycles, and the power source gradually loses output. A slower journey is not entirely safe, because time itself is another harsh environmental condition. The problem therefore cannot be solved simply by choosing the fastest or the slowest spacecraft. Each velocity creates a different kind of risk. Lower speed increases the effects of aging, while higher speed increases the destructive force of every particle and demands heavier shielding. For a gram-scale probe, extremely low mass is what makes laser acceleration possible. A device weighing only a few grams requires far less energy than a spacecraft weighing many tons. A thin sail could receive intense acceleration for a short time and carry the entire structure out of the solar system. The probe's frontal cross-section could also be made very small. If its instruments were arranged in a long, narrow structure, it would sweep through only a thin corridor of the interstellar medium. The probability of encountering a rare, large particle would therefore be lower than for a spacecraft with a broad forward face. But this advantage comes with extreme fragility. A gram-scale probe cannot carry a thick shield, multiple layers separated by gaps tens of centimeters wide, or backup compartments. Every additional gram of protective material could substantially increase the total mass and completely change the requirements of the laser system. The entire computer, camera, power source, and communications equipment must fit within a very small volume. An impact does not need to destroy the whole spacecraft. Damaging a single control chip or orientation sensor may be enough to end the mission. If the camera stops working, the probe cannot record its target. If the transmitter is destroyed, the data cannot return to Earth. If the attitude control system fails, the spacecraft may fly past Alpha Centauri with its instruments pointing in the wrong direction and miss the entire observation window. A gram-scale probe has almost no ability to repair itself. It carries no robots, replacement components, or complex mechanisms for changing damaged parts. Even if the computer detects that a component has failed, it can switch to a backup only if that backup was built into the spacecraft from the beginning. Yet, adding backup systems increases both mass and surface area. 2 cameras are safer than 1, but they require more power, memory, and space. Every decision that protects one function also makes the spacecraft harder to accelerate or creates additional surface area that dust can strike. A large spacecraft can carry capabilities that a small probe cannot. It may be surrounded by multi-layer shielding, divided into sealed compartments, and place critical equipment deep behind its forward section. Electrical, cooling, and data routes can be duplicated so that one impact does not disable the entire system. Repair robots could inspect the surface, seal punctures, and replace components designed as removable modules. A crewed spacecraft could also rely on human judgment to respond to failures that were not fully anticipated before departure. Multiple independent sensors could confirm the condition of the shielding, temperature, and pressure. If one computer failed, another system could continue controlling the spacecraft. If one compartment were penetrated, airtight doors could isolate it while the rest of the vehicle continued the journey. But every one of those capabilities has mass. Thicker shielding requires more material. Backup compartments, robots, air, water, power sources, and life support systems could increase the total mass to thousands or millions of times that of a gram-scale probe. The energy required for acceleration rises with the spacecraft's mass. Accelerating even 1 gram of matter to 20% of the speed of light is already an extraordinarily difficult task. Accelerating thousands of tons to the same velocity would require an amount of energy far beyond the present capabilities of human civilization. The propulsion system must also carry or receive enough energy to produce the required acceleration. If the spacecraft uses onboard fuel, that fuel adds even more mass. If it is driven by a remote laser, the transmitting facility must be enormous and keep the beam precisely aligned with the target throughout the acceleration phase. Shielding makes the spacecraft heavier, and a heavier spacecraft requires a more powerful propulsion system. A more powerful propulsion system demands more energy, more fuel, or larger infrastructure. Every solution to the impact problem therefore creates a new challenge in reaching interstellar velocity. The mass of the shield also affects deceleration. A spacecraft making a high-speed flyby of Alpha Centauri does not need to carry much fuel for the final stage. A vehicle intended to enter orbit or stop near its destination must remove an enormous amount of kinetic energy, greatly increasing the size of its propulsion system and fuel supply. For this reason, ultralight probes are often imagined as flyby vehicles. They trade the ability to remain near the target for high speed and a shorter journey. Every observation must be planned in advance and completed, while the distance to the star system is changing at an extraordinary rate. If the camera must turn toward a planet, the orientation system must respond at exactly the right moment. If the memory cannot record data quickly enough, the information may be lost before the spacecraft passes by. If the transmission signal is too weak, there will be no second opportunity to return to the target and repeat the measurement. A spacecraft traveling at 0.1 would pass through the star system more slowly, allowing more time for observation. Its velocity would still be enormous, but a target might remain within a useful range longer than it would for a spacecraft moving at 0.2. This could allow the camera to capture more frames, or give the guidance system more time to correct an error. However, the longer journey means the instruments must survive for another 20 years before reaching that brief opportunity. The power source must preserve enough output, the onboard clocks must remain stable, and the materials must withstand radiation for much longer. No choice provides benefits without creating costs elsewhere. The optimal velocity may therefore not be the highest speed the technology can achieve. It may lie at the point where travel time, acceleration, energy, shielding mass, and probability of survival are balanced most effectively for the mission's purpose. If the goal is only to return the first few images from another star system, an extremely light and fast probe may be a reasonable choice. If the mission requires longer observations, deceleration, or a larger scientific payload, a lower velocity may lead to a more practical design. The lifetime of the power source also affects this balance. Radioisotope power systems gradually lose output, while stored batteries may degrade after many thermal cycles. The longer the journey, the greater the energy reserve the spacecraft must carry from the beginning. The ability to transmit data also changes with the design. A small probe may reach a high velocity, but carry only a low-power transmitter and a small antenna. Its data may take years to send back, while the signal is so weak that receivers on Earth must integrate it over long periods before it can be detected. A larger spacecraft could carry a broader antenna and a more powerful energy source, but accelerating it would be far more difficult. If its velocity were reduced, the journey would take longer, and technology on Earth might change completely before the data finally arrived. The probability of survival is not an independent number. It depends on velocity, frontal area, shield thickness, and the distribution of dust along the route. A fast mission may accept a high loss rate if thousands of probes are launched at once. A crewed mission cannot accept the same level of risk. It requires a far greater probability of survival, which means thicker shielding, more extensive redundancy, and possibly a lower cruising speed. The purpose of the mission therefore determines what velocity can reasonably be considered acceptable. Cumulative erosion also changes with speed. At higher velocity, each particle removes more material, but the journey lasts fewer years. At lower velocity, each impact is less severe, yet the shield must endure those impacts for a longer period. It is not enough to consider only the number of years or the energy of a single particle. The entire column of matter along the route must be calculated, along with the shield's response, the rate at which equipment degrades, and the possibility that damage will overlap. A shield that survives the first collision may not remain equally effective after millions of impacts. Maintaining the correct orientation also has limits in both energy and lifespan. The spacecraft must use reaction wheels, microthrusters, or other mechanisms to correct its attitude. Each adjustment consumes only a small amount of resources, but over 20 or 40 years, the total number of corrections may become significant. A faster spacecraft requires greater precision as it approaches the target. It crosses enormous distances every second, so an error in timing or direction could cause the camera to miss the planet it was meant to observe. A tiny mistake made near Earth can grow into a vast separation after several light years. All of these factors make the choice of velocity a problem involving the entire spacecraft, not just its propulsion system. Speed determines travel time, impact energy, shielding mass, equipment lifetime, communication difficulty, and the precision required during the flyby. A spacecraft traveling at 20% of the speed of light may arrive 20 years earlier, but its shield must endure much more violent impacts. If the design is too light, it could reach Alpha Centauri with a clouded camera, a damaged computer, or a transmitter no longer capable of sending a signal. A spacecraft traveling at 10% of the speed of light might carry thicker protection within the same technological limits on acceleration. It would experience less energy from each impact and have more time to observe the system when it arrived. In return, every onboard component would have to keep working for more than 4 decades. Arriving early is meaningless if the spacecraft can no longer perform its mission. A fast journey succeeds only if the shielding, power source, guidance, and communication systems remain functional at the end of the route. Speed has value only when the equipment survives long enough to use it. Conversely, a slower spacecraft is not automatically safer. Another 20 years of operation may degrade its components, weaken its power source, and allow small errors to accumulate. It may be well protected against dust and still fail because of the journey's extended duration. The balance may be different for every mission. A swarm of tiny probes that can tolerate the loss of many individual vehicles may choose 0. 2C. A larger scientific spacecraft, or one that must slow down, may need to travel at a lower velocity even if that adds many years to the journey. The space ahead does not become cleaner simply because the spacecraft moves more slowly, nor does it disappear when the vehicle moves faster. Every spacecraft must pass through the same region of gas and dust. The difference lies in how it encounters that matter and how much energy is released in each collision. Nor can the spacecraft simply observe and avoid every dust grain along the way. Most particles are too small, too dark, and detected too late for the control system to respond. The vehicle must be designed on the assumption that some impacts will inevitably occur during the journey. The question, then, is not only whether 20% of the speed of light can be reached. The more important question is what kind of spacecraft can reach that velocity, how much protection it can carry, and how much of its functionality will remain after crossing more than 4 light years. If space cannot be made cleaner and individual dust grains cannot be seen from far away, the spacecraft must accept that collisions are part of the journey. Its design cannot depend on the hope that it will encounter nothing, but must begin with the assumption that its surface will be struck, material will be lost, and some systems may fail. The goal is therefore no longer to build a spacecraft that is completely invulnerable. What is needed is a vehicle designed to keep its most important components behind the shield, contain and disperse damage, preserve redundant systems, and continue flying even when part of its structure is no longer as intact as it was at launch. The spacecraft does not turn a broad face forward like a wall rushing through space. Instead, it travels along its long axis, with its smallest and best protected end pointed directly into the direction of motion. Behind that forward shield, the camera, computer, power source, and communication system are arranged in a long line, almost like components housed inside the shaft of a needle. This shape does not make interstellar gas and dust disappear, but it reduces the volume of space the spacecraft sweeps through. The smaller the frontal area, the fewer particles will follow paths that intersect the vehicle. For rare, larger grains in particular, reducing the cross-section can significantly change the probability of collision across a journey of more than 4 light-years. A spherical spacecraft, or one with a broad forward face, would intercept more material over the same distance. A long, narrow structure, by contrast, opens only a thin corridor through the interstellar medium. Dust can still appear within that corridor, but fewer grains have the chance to lie directly in the spacecraft's path. A needle-like design also allows most of the equipment to remain within the protective shadow of the forward shield. When a particle strikes the nose, the plasma and debris tend to continue moving along the original direction of travel. If the equipment is arranged compactly behind the shield, it may avoid much of the material expanding outward to the sides. However, the spacecraft must maintain an extremely precise orientation for this advantage to remain effective. If the nose shifts even slightly away from the direction of motion, the long side of the vehicle begins to face the stream of gas and dust. The frontal area may then increase many times over, exposing unprotected parts of the structure to impacts they were never designed to absorb. Shape is therefore only the first layer of protection. The nose must also contain a material that can tolerate damage without sacrificing the functions behind it. This layer is not expected to remain unchanged throughout the journey. Instead, it is allowed to lose material gradually in a way that has been anticipated in advance. Each small particle may create a crater, melt a tiny region, or remove a minute amount of material. After many years, the shield becomes thinner, but if its original thickness was sufficient, the equipment inside will remain covered until the spacecraft reaches its destination. The material acts as a protective reserve that can slowly be consumed. This kind of protection is often called sacrificial material. The word sacrificial does not mean that it is destroyed in a single event, but that part of the spacecraft's mass has been set aside to receive impacts in place of the equipment. It may become cratered, eroded, locally melted, or vaporized layer by layer without causing the entire spacecraft to lose function. Carbon and graphite often appear in studies because they can withstand high temperatures and have much lower densities than many metals. Heat-resistant ceramics may remain stable under extreme conditions, while composites allow several different properties to be combined within one structure. Even so, no material has been proven completely impenetrable at 20% of the speed of light. A material that tolerates heat well is not necessarily the best at surviving impacts. An extremely hard material may resist deformation but remain brittle, causing it to crack and produce fragments under a shock wave. A softer material may absorb energy through deformation, yet melt or lose mass more quickly. Thermal conductivity also affects survivability. If heat remains concentrated around a crater for too long, the shield may continue weakening after the particle has already struck. A material that conducts heat more effectively may spread some of the energy across a wider region, but it may also carry heat toward equipment deeper inside. Because no single material can solve every problem, the spacecraft may use several layers with different purposes. The outer layer receives the first impact and breaks apart the particle. A gap behind it allows the plasma and debris to expand, while the next layer absorbs the remaining energy after it has been distributed across a broader area. This is a natural extension of the Whipple shield principle, but applying it to an interstellar spacecraft is far more difficult than using it on a station operating near Earth. Every shield layer adds mass, and every gap requires a supporting frame to keep the structure stable. An effective multi-layer system may become too heavy for a probe weighing only a few grams. If the first and second layers are too close together, the debris cloud has no time to expand. If they are placed farther apart, the spacecraft becomes longer, bulkier, and harder to keep aligned. The design must provide enough distance for the material to disperse without allowing the total mass and size to exceed the capabilities of the acceleration system. On a large spacecraft, several shield layers could be placed in front of the main compartments, storage tanks, and life support systems. On an ultralight probe, a similar structure might consist of only a thin outer layer, a gap of a few millimeters, and a chip positioned behind it. The same principle must be reduced to the smallest scale that can still be manufactured. Some models of gram-scale probes suggest that a shield several millimeters thick could account for a few % of the total mass in certain configurations. That may sound small, but on a spacecraft weighing only a few grams, every percentage point directly affects its ability to accelerate and the required size of its light sail. The necessary thickness also changes with the frontal area, dust density, and the largest particle the design is intended to survive. Even a small increase in cross-section raises the expected number of impacts. If the dust model includes more large particles, the protective layer must become thicker, or the mission must accept a greater probability of losing the spacecraft. Even the best shield cannot provide equal protection in every direction. A camera needs an unobstructed view, an antenna must transmit signals, and a radiator must exchange heat with space. These components create regions where the design cannot simply place more thick material in front of them. One way to reduce the consequences is to avoid concentrating every function in the same location. If the camera, memory, and computer are all contained on a single chip, one small impact could silence the entire spacecraft. When those functions are distributed, damage to one region does not necessarily eliminate every remaining capability. The spacecraft could carry several small processors instead of one central computer. If one fails, the others could continue controlling the vehicle. Memory could be divided among several physical locations, so that one crater destroys only part of the data rather than every image the spacecraft has collected. Electrical lines can also follow multiple routes. If one conductor is severed, the current can be redirected through another path. Orientation sensors can be placed at several locations, allowing the spacecraft to determine its attitude even if one side of the structure has been damaged. A backup communication system is especially important because a mission has value only if its data can return to Earth. The spacecraft may use several small transmitting elements or keep a second transmitter in sleep mode. If the primary device fails, the backup can be activated as the spacecraft approaches its target. But redundancy does not come without cost. Every additional processor, conductor, and sensor requires mass, power, and space. The design must determine which functions are important enough to be duplicated, while other components can exist only as single units. For a gram-scale probe, it is impossible to duplicate everything. Adding another camera may increase the mass beyond acceptable limits, while multiple data paths make the circuitry more complex. The spacecraft must therefore prioritize the functions that directly determine its ability to observe and transmit information. A larger spacecraft can go further by dividing its structure into independent modules. Each module may have its own power source, computer, and control system. If one region is damaged, it can be isolated to prevent electrical, thermal, or pressure-related failures from spreading into the rest of the vehicle. This distribution transforms the spacecraft from a single device into a network of cooperating elements. No component is entirely independent, but the vehicle as a whole no longer relies on one vulnerable point. An impact may remove part of its capability without destroying the entire mission. Another way to distribute risk is to avoid placing every hope in a single spacecraft. Instead of launching only one vehicle, a program could send dozens, hundreds, or thousands of ultralight probes along paths that are close together but not perfectly identical. Some probes may fail during acceleration as their sails endure the enormous force of the laser. Others may lose their orientation after leaving the solar system. Still others may have their cameras clouded by dust, their memory damaged, or their communications systems severed before reaching the target. If the number is large enough, not every spacecraft needs to survive. As long as some complete the journey, collect data, and transmit their signals successfully, the program can still achieve its scientific objective. The probability of failure for each individual probe is offset by the size of the entire swarm. This approach does not stop the dust or make each spacecraft more durable. It simply prevents one collision from erasing the entire mission. Risk is distributed across many vehicles, much as data can be divided among several memory units within a single spacecraft. In some theoretical models, the probes could also relay data to one another or coordinate their signals. A spacecraft in a favorable position might serve as a relay station for another, while several small transmitters could combine their signals to make them easier to detect. These ideas would still require extraordinarily precise synchronization and orientation. The swarm would not travel through exactly the same corridor. A very small separation at the time the probes leave the solar system would grow larger over many years. A dust grain that destroys one vehicle may lie outside the paths of the others, preventing the entire group from sharing the same fate. However, launching large numbers is practical only for spacecraft that are extremely light and relatively inexpensive. The same method cannot be applied to crewed vessels or large scientific vehicles. In those cases, each spacecraft must achieve a much higher probability of survival and carry genuine repair capabilities. Whether traveling alone or as part of a swarm, every spacecraft must keep its best protected surface facing forward. Maintaining that orientation for 20 or 40 years is not simple, because the vehicle is continuously subjected to extremely small forces from many different sources. Radiation pressure from the stars may act unevenly across the surface. Electrical charge accumulating on the hull can interact with interstellar magnetic fields, producing extremely weak but persistent forces and torques. Every off-center dust impact also transfers a small amount of rotational motion into the structure. A single disturbance is almost insignificant, but many uneven impacts can cause the spacecraft to rotate slowly. Without a control system, the shielded nose would gradually drift away from the direction of motion, exposing the side surfaces or optical equipment directly to the stream of matter. The spacecraft could use small reaction wheels, movable masses, microthrusters, or electromagnetic interactions to correct its orientation. Each method has limits in energy, lifespan, and precision. The system must continue operating for decades, with almost no immediate assistance from Earth. Control signals from Earth would take years to reach the spacecraft once it was near its destination. Every short-term correction must therefore be performed autonomously. The computer must recognize the misalignment, evaluate the danger, and return the shielded face to the correct position before the unprotected body begins to erode. Maintaining orientation is also critical during the observation phase. The camera must point toward the target while the shield continues protecting the spacecraft from the incoming stream of matter. These two requirements may conflict if the instrument is fixed to the body and cannot look sideways without rotating the entire vehicle. One design could place the camera behind a small viewing port or use mirrors to redirect the incoming light. Another could allow the instrument to rotate independently, while the spacecraft's body keeps its shielded nose facing forward. Every moving mechanism, however, adds complexity and creates another possible point of failure. The light sail is a surface that requires particular control after the acceleration phase. If it remains deployed, it may increase the frontal area enormously. If it is folded away, the mechanism must operate correctly after enduring force, heat, and vibration during the spacecraft's departure from the solar system. A sail that fails to retract completely could cause the spacecraft to rotate or pull its body out of alignment. The thin material is also easily punctured by dust, creating holes that make radiation pressure uneven across the surface. Minor damage to the sail could develop into a persistent attitude error, lasting many years. Beyond shielding attached directly to the spacecraft, some theoretical concepts propose creating a protective region ahead of the vehicle. The spacecraft could release small particles of material in the direction of travel, forming a thin cloud at a certain distance in front of the main body. If interstellar dust struck this cloud first, the incoming grain might be broken apart, heated, or ionized before reaching the spacecraft. The main body would then encounter smaller, more widely dispersed fragments, much like the way the bumper in a Whipple shield processes an object before it reaches the rear wall. A large distance between the protective cloud and the spacecraft could give the plasma and debris more time to expand. In principle, this would help spread the energy across a broader area, maintaining a stable cloud in front of a vehicle traveling at zero. 2C, however, would be an extraordinarily difficult challenge. The protective material must also be accelerated to nearly the same velocity as the spacecraft. If it moves even slightly more slowly, the spacecraft will quickly catch up and pass through it. If it moves faster, the cloud will gradually pull away and no longer cover the correct corridor ahead. The particles within the cloud would also be affected by electrical charge, radiation, and the interstellar environment, causing them to disperse over time. The spacecraft would need to keep replenishing the material or adjusting its position, increasing both the stored mass and the energy consumed during the journey. A cloud that is too dense could also become a danger. If the spacecraft catches up with the protective particles at a sufficiently high relative velocity, those particles will strike the nose themselves. The system would have to control the material's speed with extraordinary precision to avoid creating an artificial stream of dust directly ahead of the spacecraft. Because of these challenges, a protective cloud remains more of a research concept than a technology ready for use. Yet it reveals an important way of thinking. The spacecraft does not necessarily have to wait for a dust particle to reach its hull, but may instead try to disrupt the object from a greater distance. Electric and magnetic fields have also been considered for a similar purpose. Protons, electrons, and ions in interstellar gas carry electrical charge, so their paths can be bent as they pass through a sufficiently strong field. In theory, a field extending ahead of the spacecraft could deflect part of the incoming particle stream away from the leading edge. Dust grains, however, do not always carry a stable electrical charge. A neutral particle responds very little to a magnetic field, while a large grain has too much inertia to be redirected during the brief interval before impact. The charge carried by dust can also change as it absorbs light or interacts with plasma. To deflect a particle far enough, the spacecraft would need to detect or influence it from a great distance. At 20% of the speed of light, every kilometer ahead represents only a few tens of millionths of a second. A weak field would not have enough time to produce a meaningful change before the particle reached the surface. A stronger field would require coils, magnets, power supplies, and cooling systems. These components would increase the spacecraft's mass, while the energy demand could exceed the capabilities of a gram-scale probe. A larger spacecraft would have more room for such a system, but it would still require extremely high power. A magnetic field therefore cannot be treated as an invisible shield that pushes every dust grain aside. It may help deflect certain charged particles and reduce part of the high-energy gas stream, but it cannot replace physical shielding against neutral dust or larger grains. A practical design may need to combine several methods rather than depend on a single solution. A long, narrow shape reduces the number of impacts. Sacrificial material absorbs erosion. Gaps between layers disperse fragments, while redundant systems allow the spacecraft to continue operating after one component has been lost. Multiple spacecraft can be launched to distribute risk across the mission. Attitude control systems keep the shielded face pointed in the correct direction. Electric or magnetic fields may reduce part of the charged particle stream, while forward protection concepts attempt to disrupt objects before they reach the main body. Each layer of protection removes only part of the danger. Together, they may raise the probability of survival to an acceptable level, but they cannot provide an absolute guarantee. No spacecraft can be designed to withstand every dust particle that might exist in space. Calculations of shield thickness always begin with a model of the environment. That model estimates gas density, particle size distribution, dust composition, and the total column of matter along the route. Engineers then select an acceptable level of damage and determine how much protective material must be carried. If the actual density is lower than predicted, the spacecraft will arrive with much of its shield still intact. If the environment contains more dust, the material may be consumed too early. Even a small difference in the rare, large particle tail of the distribution can greatly alter the probability of a destructive collision. This is why a shield several millimeters thick in one model cannot become a universal value for every spacecraft. A change in shape, frontal cross-section, or velocity will change the result. A new route toward a different star would require the environment to be evaluated again from the beginning. Every design is based on what humanity believes lies within the darkness between the stars. Average values may describe billions of small particles well, but they cannot reveal the position of each rare, large grain. Those exceptions may determine the fate of an individual spacecraft. After several decades, the forward shield is covered with countless craters. Some of its material has vaporized, while other regions have been heated and structurally altered. behind a protective layer now considerably thinner than when it left Earth. The camera, memory, and transmitter are still functioning. The destination star now shines more brightly on the sensors. The spacecraft prepares for the most important observation period of its entire journey. Systems that have slept for years begin to awaken, run their checks, and turn toward the target. Yet ahead still lies a region of space that cannot be mapped particle by particle. Somewhere in that darkness, there may be an object larger than average, giving off no light and leaving too little time for the camera to detect it. It does not appear clearly in every number used to design the shield. The spacecraft was built on the assumption that collisions would inevitably occur. It reduced its frontal area, carried sacrificial material, distributed its systems, and kept its nose pointed forward. Yet every protective measure must ultimately face the same question. What happens if the next particle is larger than anything the designers predicted? The spacecraft has been traveling for nearly 20 years since leaving the solar system. Behind it, the sun has become a small star among countless other points of light. Ahead, Alpha Centauri is no longer a single bright dot, but is gradually resolving into a true star system, with separate sources of light moving across the sensors. Instruments that remain dormant through most of the journey begin to awaken. The camera is warmed to its operating temperature, the memory is checked, and the onboard clock resynchronizes the entire observation schedule. Every system that has survived nearly 2 decades is preparing for the brief period that will determine the meaning of the entire flight. At nearly 20% of the speed of light, the spacecraft cannot stop to observe for longer. It will race through the star system at tens of thousands of kilometers per second, collecting whatever data it can before continuing into the darkness beyond. There will be no second pass and no opportunity to return if the camera points in the wrong direction or an instrument stops working. The space ahead of the spacecraft still appears completely empty. The camera sees no object large enough to avoid, and radar cannot detect every small particle along the path ahead. Yet somewhere in that darkness, there may be a dust grain that emits no light, produces no signal, and reflects too little light to be detected from a distance. The particle may be almost motionless relative to the interstellar medium. It is the spacecraft that is rushing toward it at nearly 60,000 kilometers per second. A distance of 1,000 kilometers disappears in less than 2/100ths of a second, while the final kilometer lasts only a few tens of millionths of a second. There is not enough time for the camera to recognize the particle, send the information to the computer, calculate an evasive path, and turn the entire spacecraft in another direction. If the collision occurs, its outcome has already been decided before any system can understand that an object lies ahead. Everything now depends on the particle's size, where it strikes, and the layers of material standing between it and the equipment inside. If the dust grain is extremely small, the result may be nothing more than a flash that no human being will ever see. The particle strikes the sacrificial shield at the spacecraft's nose, causing a tiny region of material to be compressed, melted, and vaporized almost instantly. A small crater appears on a surface, already carrying millions of other impact marks. The energy is absorbed within the first few layers of material, while the plasma cloud expands outward or is dispersed before it can travel deeper into the body. The shield loses another tiny amount of matter, but the camera, computer, and transmitter behind it remain intact. The spacecraft experiences no meaningful loss of speed and does not drift from its path. No serious alarm needs to sound. A vibration sensor may record an extremely brief impulse, and then every reading returns almost to normal. The damage becomes part of the surface layer that was designed to wear away throughout the journey. In this case, the shield has performed exactly as intended. It has not remained pristine, but remaining pristine was never the goal. What matters is that the material allowed to be sacrificed received the impact in place of the irreplaceable equipment behind it. The spacecraft continues forward, and the camera remains pointed toward Alpha Centauri. A few minutes later, the optical system begins capturing its first images. A dust particle has struck the spacecraft, but it was neither large enough nor positioned precisely enough to alter the fate of the mission. Another possibility differs by only a few millimeters at the point of impact. The particle is still not large enough to tear the entire spacecraft apart, but it strikes a gap between two shield layers or lands near a region that has eroded more severely than expected. Secondary fragments may then find a path deeper into the structure. The spacecraft retains its shape, and its trajectory changes very little. Yet a hot fragment may sever the power line leading to the camera. An electrical pulse formed within the plasma may damage the memory, or a smaller fragment may penetrate the laser transmitting element. From the outside, the spacecraft continues racing through the star system as though nothing serious has happened. It does not break apart or transform into a large cloud of plasma, but the observation system may have lost its ability to see, while the communications equipment can no longer send data back to Earth. An interstellar mission does not need to be completely destroyed to be considered a failure. If the camera no longer functions, the scientific objective is gone. If the memory fails, the images just recorded cannot be preserved. If the transmitter stops working, all the data still stored aboard the spacecraft becomes meaningless to the people waiting on Earth. In that case, the spacecraft still exists structurally but has died functionally. It may continue traveling for millions of years, carrying components and data that will never be read again. There is no great explosion, only a silence that begins immediately after an impact too small to see. A third possibility lies within the rarer portion of the interstellar dust environment. The particle ahead is much larger than the average value used in the design. It is still extremely small by ordinary standards, but the mass concentrated within it is enough to carry enormous energy when it strikes the spacecraft at relativistic velocity. The first shield layer is penetrated or vaporized across a wider region than expected. The particle and surface material become a cloud of hot plasma, while fragments continue deeper into the layers behind before they have time to spread sufficiently. Shock waves travel through the entire small structure, exposing several closely packed components to the load at once. In a spacecraft weighing only a few grams, there is little distance between the shield and the equipment. The camera, processor, memory, and power source may be separated by only a few millimeters. A debris cloud penetrating the nose could therefore damage several systems almost simultaneously. The spacecraft may split into several pieces, or it may retain its shape while losing all electrical power. If the power source fails, the computer and sensors stop working at the same moment. If the structure is knocked out of alignment, the antenna no longer points toward Earth, even if some of the data remains stored in memory. For a gram-scale probe, this collision may end the journey completely. There are no repair robots, no backup compartments, and no second set of equipment placed far enough away to continue the mission. A rare dust grain has exceeded every safety margin the shield could provide. This does not mean that every interstellar spacecraft will be destroyed by such a particle. The probability of encountering a large grain depends on the frontal area, the distance traveled, the dust density, and the true particle size distribution. The smaller the spacecraft, the narrower the corridor it sweeps through, reducing the chance of meeting a rare particle. But a low probability does not mean impossibility. A mission launching only one spacecraft may fail, even if most similar routes would have been safe. That uncertainty is precisely why sending many ultralight probes may be more reasonable than placing every hope in a single vehicle. For a large, crewed spacecraft, the same impact could lead to a different outcome. The forward shield would be thicker, the compartments separated, and the most important equipment buried deeper within the structure. A single dust grain would be less likely to destroy the entire vehicle with one strike. If the object penetrated a less important storage compartment, the system could close airtight doors and isolate the damaged area. Robots could inspect the site, apply a temporary patch, and assess the remaining structural strength. The crew could move supplies into another compartment and continue the journey with less reserve space. A large spacecraft also has multiple electrical routes, several computers, and more than one cooling loop. The failure of a single system does not mean that every function stops. Redundant design allows the vehicle to lose part of its structure while still preserving navigation, maintaining its atmosphere, and protecting the people on board. Even so, the location of the impact can still determine the outcome. A puncture in the outer shield is entirely different from a strike on a fuel tank, the main radiator, or a load-bearing joint. A dust grain does not need to penetrate the living compartment to create a failure that threatens the entire spacecraft. If the primary cooling system is destroyed, heat from the power source and onboard equipment can no longer escape. If a fuel tank is punctured, the spacecraft may lose its ability to correct its trajectory or slow down. If a structural support develops a crack, prolonged stress may allow the damage to spread for days after the collision. The greatest danger comes when the particle strikes a system the spacecraft cannot replace. A life support loop may have a backup, but the vehicle still has a limit to how much damage it can endure. Every compartment lost and every redundant system brought into service reduces the safety margin for the years that remain. A collision, therefore, does not necessarily kill a crewed spacecraft immediately. Instead, it may begin a prolonged struggle to keep pressure, temperature, electrical power, and control within survivable limits. The outcome depends on where the impact occurs, how quickly it is detected, and what capabilities remain after the event. The original question, then, has no single answer that applies to every dust grain and every spacecraft. Yes, a sufficiently large particle can destroy an interstellar vehicle, especially if that vehicle weighs only a few grams and is traveling at 10 or 20% of the speed of light. But most smaller grains will not instantly tear the entire structure apart. Many particles will cause only localized damage, heating the surface, carving out a crater, or removing part of the shielding. Individual impacts may not end the mission, but they contribute to the cumulative erosion taking place throughout the journey. The danger begins with the particle's mass, because a dense grain contains more material than a porous one of the same size. The spacecraft's velocity determines how much kinetic energy is released, while the impact angle affects whether that energy drives deeply into the structure or is carried along the surface. The frontal area determines how much space the spacecraft sweeps through and how many particles it is likely to encounter. The shielding material influences how the grain breaks apart, while the spacing between layers determines whether the debris cloud has enough time to expand. The point of impact may matter as much as the total energy. A particle striking a thick shield may leave only a scar, while the same particle hitting a camera, power line, or structural joint could end the entire mission. The type of spacecraft determines how effectively the damage can be isolated or repaired. The duration of the journey also changes the outcome. A shield at the end of its 20th year is no longer the same shield that left Earth. Old craters, heat-altered regions, and microscopic cracks gradually change how much stress the surface can withstand. In the end, every calculation still depends on the true distribution of dust along the route. Most of the environment may be described by average values, but a rare, large grain does not appear clearly within those averages. It may lie directly in the path of one spacecraft while remaining outside the paths of thousands of others. Humanity already has data on micrometeoroids near Earth and artificial debris in orbit. Impact scars on space shuttles, satellites, and the International Space Station show that small objects can produce damage far greater than their size would suggest. Laboratories have fired tiny projectiles into spacecraft materials at several kilometers per second. These experiments show that particles can melt, vaporize, create plasma, and cause the inner surface of a shield to break apart even when they do not fully penetrate the outer layer. Astronomers have also built models of interstellar gas and dust by studying how light is absorbed and scattered. Computers can simulate how protons, electrons, ions, and dust interact with materials at high velocity. These data allow engineers to estimate shield thickness and the probability of survival. Yet an enormous gap remains between these models and an actual flight. No spacecraft has reached 20% of the speed of light. No shield has been tested against a macroscopic dust particle moving at nearly 60,000 kilometers per second, and no vehicle has completed the journey to Alpha Centauri. There is no complete map showing the position of every dust grain along the route. There is no direct data describing how glass, mirrors, or shielding materials will look after 20 years of bombardment by interstellar gas at relativistic velocity. Current estimates still rely on indirect measurements and physical models. Nor does humanity possess a proven protective system for a crewed spacecraft traveling at such speeds. Whipple shields, sacrificial materials, compartmentalized structures, and repair systems all have value, but none has been carried through the interstellar medium at the required velocity. The honest answer, therefore, is neither an absolute claim that dust will certainly destroy the spacecraft, nor a guarantee that present-day shielding will solve every problem. What can be said with confidence is that speed transforms tiny amounts of matter into a danger that cannot be ignored. The hypothetical spacecraft is still racing toward Alpha Centauri. The dust grain ahead strikes the shield in a flash too brief to form a complete image. A thin layer of material disappears from the nose, while the plasma cloud expands and cools into the darkness. The sensors check the condition of the camera, computer, and transmitter. Power remains stable, the clock continues running, and the guidance system detects no significant change in orientation. The impact has removed part of the protective layer, but it has not reached the equipment behind it. The camera remains open as the spacecraft moves deeper into the star system. Points of light on the sensor gradually separate from one another, while the computer begins storing the first images ever captured from a distance closer than any human-made device has reached before. The data is compressed, divided into several parts, and sent to the transmitter. A faint beam is directed back toward the region of the sky where the sun has become only a small point of light. The first photons begin a journey lasting more than 4 years back to Earth. The space between the two stars was never completely empty. It contains gas, dust, and objects too small to see, yet powerful enough to change the outcome of a mission lasting several decades. There is no perfectly clean path that a spacecraft can follow without ever being struck. The challenge of interstellar travel is therefore not to find a corridor with no dust at all. Such a route may not exist, and it could never be inspected particle by particle before departure. What matters is creating a vehicle that can continue functioning after its surface has been hit. The spacecraft must accept the gradual loss of material, endure countless small craters, and survive some events more severe than expected. It must protect its critical equipment, contain and disperse damage, and preserve enough ability to see, think, and communicate at the end of the journey. A tiny dust grain can destroy an entire interstellar spacecraft if it is large enough, if the velocity is high enough, and if the impact occurs at the most vulnerable point. But the success of the mission does not depend on never encountering dust. It depends on whether the spacecraft can continue to exist after that encounter. And in the darkness between the stars, survival may sometimes be decided not by whether the shield remains intact, but by whether the camera behind it is still open.